I still want to get like contents.
All right. Good morning, everybody. Thank you for coming. Thank you especially to guests not from Munich Rocketry. We really appreciate you coming out on a Saturday to come out and give us advice and critiques on our designs, and we're excited to present and get your feedback. Welcome to the critical design review of the Andúril-1 rocket program. This is the rocket we're building this year for Launch Canada 2024, which will be occurring in August in Timmins, Ontario. Next slide, please. If you are interested in filling out our minutes or seeing what's happening in the minutes, feel free to join, make additions. This is, as a reminder, we are literally doing rocket science. Mistakes will be made. It is challenging, but this is what we're here for. We're here to learn how to do this, how to be good engineers. And this is what we're practicing before we head off into our eventual careers, possibly in the field. And so if you have any concerns, sorry, not quite ready yet. If you have any concerns with any part of your project, this is the time to bring that up. We are all here gathered together, different divisions, lots of different eyes on your project. This is the best time to catch things. Next slide. So this design review will be focused, as I said, on the Andúril-1 flight vehicle, which is the rocket that we're building this season, and we'll be flying at Timmins, Ontario, Launch Canada 2024 in August. We're looking for evidence that your designs have been developed and reviewed within the divisions. This includes testing plans, analysis, and failure notices, stuff like that. Making sure that all your design decisions are well justified. And if you're behind schedule, this is the time to bring that up if you haven't already. Again, we're all here to help as a team make sure that these projects and the overall program progresses well and represents the best work that we can possibly do. We're going to start with an overview of the rocket itself, mission objectives, etc., and then move into the recovery system, highlighting that since it is one of the most critical and important projects on the rocket. We need to make sure that it goes up well and then it comes down safely and survives the landing. We'll then go into the airframe, overall, how the rocket's built, how we get that recovery system up, and the payload, etc. Payload itself will be included in the avionics section at the very end when we talk about the flight computer, the telemetry systems, how we communicate with the rocket during flight. Next slide. So we're going to start with the mission overview and rocket specifications from our lead engineer, Gordon.
Okay, thank you, Scott. So let me just introduce our whole mission statement. So our whole mission statement is to gain experience in a well-managed design cycle that with a rocket fly in the supersonic regime. We choose this mission statement because we have quite a bit of program problem last season, which we want to address and build the team back to a standard that we can execute projects without thinking that much or having too much problem. So that's why we choose this scope. So we're targeting 30,000 feet. It's roughly 9 kilograms above ground level, and this will be a single stage using a commercial off-the-shelf solid motor, and we will be flying under supersonic regime. So in terms of concept operation concepts, we'll first assemble the rocket, and then it will be placed on the launch rail, which will be ignited with the launch safety control officer, and then the rocket will start lifting off until it reaches max speed. So after max speed, all the fuel brain will be burnt, the motor would not provide any more thrust, so the rocket will start decelerating, and it will coast up to apogee. After apogee, we'll deploy our Nosecone. It will be attached to the rocket, and then we deploy our first drop parachute to slow down the rocket. And then when the rocket descends to 1,500 feet, we deploy the main parachute to further slow down the rocket to our target velocity. After touchdown, our recovery team would go and get the rocket back to home. So this is a cross-section of the current rocket design. So we first have our aerostructure components. Click on up would be a solid motor casing with the choice of our fuel brains, and then it will carry our payload and avionics, and finally it will be recovered by our recovery system. And the total length is around 120 inches, 3 meters ish, and then here's a explosive field at the end. So we just introduce all our system today, and at the end, we'll conclude how we put everything together, since that's a very important thing during competition is assembly. So now we'll hand it off to MacLeod of Flight Dynamics and as a speed.
Thanks, Gordon. So I'll just be quickly going over the flight dynamics for the rocket. So this is our current trajectory simulation for the rocket. So you can see the blue graph here is the altitude as a function of time. The orange is our velocity, and the yellow here is acceleration. So you can see during the first 3.5 seconds is our acceleration period under thrust. And during that 3.5 seconds, we reach a max speed of Mach 2.2. And from there, you can see we're just drag and then coasting up to our altitude just above 30,000 feet. Next slide, please. Another critical aspect of the flight dynamics of the rocket is our stability simulation. So because we can't use active control or guidance on our rocket, we have to control it passively, like basically throwing a dart at a dartboard. You need to have the center of mass, which is represented by that blue dot there, in front of the center of pressure, which is the red dot. And so you need to have that in front, because otherwise, if the pressure is in front, the rocket will flip around and it will be flaming end forward, pointing end backward, which is what we call not ideal. So yeah, we've got to keep that between 1.5 and 6 cal behind the center of gravity, cal being the outside diameter of the rocket. So basically we need to keep it between that 1.5. Before that point, it's understable. After 6, it starts to get overstable and snap around in the wind. So you can just quickly, you can see with the 0 km/h wind, we've got nice stability margins. And then in our max wind speed of 25 km/h, you can see the margins a lot closer to the lowest point and a lot closer to the highest point. So next slide, please. This is the bending analysis that was done on the rocket. It's a great calculator that was recently built by Gordon. So you can see the max bending moment on the rocket is 350 Newton meters, and the maximum shear we will experience is 535 newtons. And you can see the maximum force happens just below the coupler on the lower fuselage. Next slide, please. So recent design changes. The initial motor we spec'd, unfortunately, was not in stock. So we had a choice between a larger and a smaller motor. The larger motor was a lot more stable and gave us the flexibility to fly in higher wind conditions, also gave us more design flexibility. However, it did cause much higher loading and stresses on the structure of the rocket. We ran some simulations and did some testing on a test fuselage, which you can see there, and it passed all the tests, so we decided it was best to go for the bigger motor as it offered us more design flexibility. Those graphs are not to scale, but you get an idea of how big they are based on that number is the average thrust in newtons of the motor. So the large one is quite considerably larger. Next slide, please. The other change that was made recently is, in order to accommodate the larger motor, we have decided the lower fuselage should now be carbon fiber, which means the antenna that we design will have to go above that region so it can correctly transmit. It also needs more space so that it can transmit. So that's required a length increase and a weight increase, which has had some effects on the flight stability, which I'll go over in the next slide. Okay, good to know. So yeah, so you can see the effect it's had on apogee max speed and max acceleration, which is neither good nor bad. It's going to be, so with the current design, so with the antenna moved and giving it more room, it's going to be slightly slower and not go quite as high. However, the main thing we're interested in is the speed off the rail, because that determines our stability. Because the faster we go, the more effect our fins have on that drag and stability, which I was talking about. So you can see here our minimum and maximum stability. And the main thing we're looking at here is not so much how stable it is, but the difference between the minimum stability and the maximum stability. It's very easy to make the rocket more stable or less stable just by changing the size of the fins. However, the difference between those numbers is very hard to change. So the first number is too small and the second number is too big. There's no way of fixing that. So ideally, we'd like the smaller window. However, we can accommodate the antenna. It just gets close to our understable and overstable points. Also has an effect on fin flutter factor of safety, not a large effect, and the bending has gotten slightly worse. So right now, given our current simulation, is flyable with the antenna, but if we run more simulations or some more designs change, and anything changes, we will move to the backup design where we shorten the fuselage and the antenna will not be able to transmit. Questions and concerns. So this is just stuff that I've been thinking. So far we've been overlooking these things. I'd like to get your input as to whether you think these are things we should be looking into and how we should look into them. First of which is, should we consider dynamic compressive loading at motor ignition? So you can see here, this is the graph of the force of the motor over time. And you can see this is 0.2 seconds. And it goes very quickly to 7,000 newtons. So right now we are doing our testing using static loading because it's much easier to do and we have a process for doing it. However, we're not sure the effect of that rapid compression is going to have. So interested to hear your thoughts on that. Also want to talk about the aerodynamic implications of radial holes at high speeds. So we have to drill holes into the fuselage to kind of secure everything in the rocket. So everything's attached to the fuselage through these holes. But obviously traveling at high speed, there's some concerns about how the airflow on those holes will affect our stability. Also want to discuss the vinyl wrap security at high speeds, because I know I've watched some rocket launches where I've seen stickers peeling off the sides. Not sure how big of a concern that is. Also, the bending calculations we did, we assumed a 50km/h maximum wind gust and just essentially said, we're moving this fast this way. If the wind comes in at 50 km/h this way, then there's your angle of attack. So I want to see if we've overlooked anything with that angle of attack and whether there's any contributors to that which we should be aware of. And then also the drag use fin feet, because right now in our simulator, we set up the fins in the simulation, but we've not figured out a way to set up the fin feet. So we just want to determine whether it's worth running an ANSYS to figure out the effect those are going to have on stability, because if they cause more drag at the bottom of the rocket, there's a risk we go overstable and have more than 6 calibers of stability. So if there's any questions about any of the other slides or feedback on any of these points, I'd really appreciate that.
We have one question from Dave Matlock in Zoom. Is there a safety factor already applied to the min stability 1.5?
Yes. Yeah, that's the that's from competition. That's their like absolute minimum value that we can have. Because ultimately, like the rocket will fly if it has a stability less than that. So yeah, the rules for competition state that it has to be no less than 1.5, and that is the factor of safety included in it.
You said that the larger motor makes the rocket more stable. Could you explain how it does that?
Because essentially what happens is it accelerates faster off the rail. So you can see the effect that speed off the rail has. Because it accelerates so fast, we're already moving fast off the rail. So that the drag from the fins is already kind of taking effect. So it means there's much less difference, like we were talking about, between the minimum stability and the maximum stability. So yeah. That's kind of where we're at the moment. Yeah.
What kind of testing have you been doing on static testing instead of the dynamic compressive loading? Because your strain rate is going to be extremely high.
Yeah.
Going from 0 to almost 7,000 newtons in that amount of time. Have you done any testing on what your actual strain rate is going to be?
No, we haven't. We should look into that. And someone put that in a minute, looking into the strain rate. Into the dynamic loading. Yeah.
How did you calculate the factor of safety for the flutter?
Sorry?
How did you calculate the factor of safety for the flutter?
There's we use a calculator. It's just hand calculations, but it's the NACA 4197. 4197. It's a technical document that's been the standard for years in terms of determining the fin flutter on our fin profile. So that's what we've been using so far. And if we think it's necessary at some point later, we will run probably some ANSYS sims on it. However, right now we've just been using that NACA report.
So we are talking about supersonic flight here, right?
Yes, yeah,
So when you cross the sonic boom, there will be compressed, there will be sort of waves of shock waves,
mhm.
and you take those into account as well.
Is that in the NACA? Do we know?
I don't think that's standard, consider shockwave, it's more consider like explosive effect.
Alright.
Maybe like
That's good, yeah, okay, but that's something to be aware of.
Hmm. Yeah, we'll look into that and we'll do that. Probably worth running ANSYS sims on that.
Yeah.
To make sure. So yeah, that's something we'll take into account. That's a good point. Any other, yeah,
I'm just curious, you mentioned if you have to move the antenna, you're not gonna be able to communicate from it. How is that gonna impact your on-off screen communications?
yes. So essentially what happens with that is we have two antennas. We'll go over that more in the avionics section, but one of those is in the Nosecone, and that's a cost. So we buy it, and it's essentially guaranteed to work. So that's what we use for all the essential information. The antenna we were discussing in the body is designed by us, and it's not flight critical because it's not transmitting like the flight critical data. That antenna is a completely separate system in the Nosecone. This is just like something that we do and would be ideal to fly, but it's not flight critical. Okay. Any other questions on incidents? Okay. Oh, yes.
Yes, you asked if you consider dynamic compressive loading, like higher order terms than acceleration, so like jerk and higher derivative terms. That would be, I guess, important for some things, I guess, based on what's inside and the structure, but I don't know how that would be done to consider it. I guess you could find like the peak load, kind of like you're doing, and try the static study, but it's an interesting point if you're able to even consider that with a hand calculation or things to do some simulation. But, yeah, that could be a scary amount of force going in if it's a higher order than acceleration.
Yeah, I think that's what we'd like to do at some point is like the current kind of testing plan is we've already done bending tests on that fuselage. We're currently trying to create a testing plan for what to do with that fuselage there. And one of them was just going to be like a static compressive load using an MTI machine. But what we're kind of becoming more tempted to do now is figure out a way, we've not figured it out at the moment, but figure out a way to just have like some sort of mass moving and just like kind of hit it on the end and figure out how to get something similar at least to this level of acceleration and jerk like you mentioned. So that's something I think definitely if you guys think that's valuable, I think that's something we should look into. So yeah.
I know that the biomed lab or there's a lab.
The
And
advanced
the,
manufacturing
that has-
facilities lab, that's the
Yeah.
drop tower.
Exactly. So maybe we should consider that, find out who is in charge of that machinery.
Yeah,
That's Denizens Machinery, but Aaron Bryce is the one who no longer works with it.
Excellent.
okay,
What's his name?
Aaron Bryce is the
Aaron
person
Bryce.
you want to talk to about
Sounds
that.
great.
okay. Yeah, we will definitely reach out to those people because I think that's definitely something I was concerned about. I just want to make sure like that's something worth looking into, but it sounds like it's worth looking into, and we'll definitely look at like the dynamic aspect of that rather than just viewing it as a solid, like a constant force. Yeah,
And you were talking about how radial holes would affect your aerodynamic implications at high speeds. Would you also want to consider the bolt holes in the fin feet as well?
yeah, that's something we're gonna have to look into is all the different holes on the rocket. So obviously you've got the radial holes like throughout the length of the fuselage. And then I think what we're talking about now is like you can see on this fin here, this is one of our old fins, and you can see these holes along the side and the impact they're gonna have as well. So yeah, that's a good point. That's something to look into. Is because these are not just like holes in the side, they have like a profile obviously into the side profile of that thing. Yeah, that's a good point. We'll look into that. Yeah.
I will say that for the overstability side, the fin feet. The reason why overstability is a problem is because of wind shear as you're going between the different layers of the atmosphere, right? So ideally, you don't want to be overstable because you'd rather the rocket be pushed and keeping its vertical orientation as it's pushed by the wind, so that when it encounters the next wind, like, you know, the next body of air that maybe is moving in a different direction, the rocket moves back rather than bending and rotating in the wind like an arrow. So I don't think that for overstability, those fin feet will be a problem because they're completely within the you know, horizontal or the within the cross-sectional area of the fin is looking from the sides.
Yes.
So they will contribute to actual stability because it'll
Yeah.
make it, you know, will be like a little parachute, but I doubt that it will have any negative contribution to the overstability.
Okay. That's a good call. Okay. Anything else? Yes.
What are the alternatives to the vinyl wrap if security is an issue at my students?
We were discussing like paint. I think Scott was looking into that. We were discussing paint for a while.
Yeah, a lot of our rockets have been painted, especially we did fly a supersonic painted rocket. Most recent two have been wrapped, and we can still do stickers for like the sponsor logos and things, more complicated designs. But given the amount of radial holes that we're gonna have and places where there's gonna be little leading edges of the wrap, it's probably not worth the risk of a little bit of pocket of air forming excessive drag on one side and then the consequences that could have just to save time on paint.
Sounds good. I'll hand it off to, wait, the recovery now? Yes.
Hello, everybody. I'm Ezekiel. I'm going to be talking about the recovery bulkhead. Before I start, I did just want to shout out Ryan. I'm not going to get him to come present with me, but he did put a lot of work into this as well. So I just wanted to shout him out for that. But in essence, what the recovery bulkhead does is at apogee, it's going to pop off the nose cone by pressurizing the upper fuselage, which will then pull out the drogue chute. Upon ascent, it's going to release the main chute via release pin system, which will hopefully slow down the rocket so that it doesn't ballistically land. Next slide. So in terms of requirements, the main requirements are those features that anything above 1,500 feet requires a dual deployment system. So it has to have both the drogue chute as well as a main chute. Additionally, the drogue chute must be deployed at apogee, and then as soon as it reaches 1,500 feet or below, the main should be deployed. In terms of design, so the overall design features two release pins here that link up and the rotether, and the drogue chute is then attached to that. At 1,500 feet on its descent, those pins are then actuated and sent into the bulkhead, which if either one of them goes, it will release the drogue chutes linked to the bulkhead, which will pull out the main chute. Changes since the PDR is that we've changed the locations of the features for the pins here. They used to all be on the underside of the bulkhead, but they're now going to be switched to the top side of the bulkhead because we found that we could have easier manufacturing methods and it could create a better seal. We also changed the Raven 4 battery mounts to be made out of aluminum sheet metal, which will be easier to manufacture as opposed, or lighter and quicker to manufacture as opposed to 3D printed plastic. We're going to be using penetrators, which are these blue screws here. So there's going to be 4 that run through the bulkhead. 2 of them are going to go to the black powder cups for pressurizing the fuselage, and 2 are going to go to these release pins. here, which also have penetrators to make sure there's a good seal for those. And then overall, the design was changed to have fewer through holes to create a better seal, so now it's only gonna have those 4 penetrators running through, which should be sealed ideally. Next slide. So here's a cross section of the penetrators. So this is what it's gonna look like. It gets the wires through the bulkhead while creating a seal. Yet again, there's those 4 that runs directly through the bulkhead to the black powder cups and the release pin charges. And those are wired to the Raven 4 altimeters on the underside of the bulkhead. We can also go to the next slide. So here's a underside view of it. So those Raven 4 altimeters handle apogee deployment as well as main chute deployment. So these 2 closer ones here will go directly to the black powder cups. Those 2 further penetrators will go to the release pins. In terms of manufacturing, we decided to go with aluminum. So because we have a lot of manufacturing experience with the club, it's FDA validated to handle the loads that we're expecting, as well as its relatively low density, which makes it light, which is ideal for Rubik's Supersonic. Manufacturing wise, we're going to attach a piece of aluminum round stock to a lathe, mill it down to 4.5 inches diameter, and then add the O-ring roof on that. So additionally, the other features are going to be attached or created on a 3-axis CNC mill, where we attach the bulkhead to a fixturing plate, and then all the radio features will be created using it. In terms of the battery mounts, we're going to be using a water jet to cut out the shapes in a 16 gauge aluminum sheet metal, and then we'll bend those into shape using brick. In terms of assembly, it's techno Lego. It should all just screw directly into the bulkhead there. So all of the features will slide in. These pins, you can just slide the pins into shape and then put the shear pins in there. Additionally, the only other thing we do need to consider is that when we are assembling the bulkhead prior to its integration into the actual fuselage, we do need to make sure we attach the parachutes prior to putting it in, otherwise it's going to be hang. In terms of integration, so the main parachute directly links to this idle up there, and then the drogue chute is held on by these 2 pins here by a tether that goes in between them, and then the upper fuselage will also interact with it by a radial screws that should just screw into it. So overall, we're going to be doing 5 main tests. So we're going to be doing a bending test on the drogue and the main chute, as well as a nose cone injection test, a release pin actuation test, as well as a seal test. So in terms of the bending failure test, we're going to fix the bulkhead to a tensile testing machine, and then just load it to 1.5 times the expected loads at the given integration points. Currently, it looks like it should be good on the FEA. And in terms of nose cone ejection, we're just going to pressurize the fuselage and see how much black powder we need to properly do shear failure on the MacLeod screws there. In terms of the actuation test for the release pins, we're just going to hang the mass of the rocket from those release pins, actuate them to see if it works properly. And then in terms of seal test, we're going to just put it in the bulkhead, seal up what we know is going to be sealed, and then pour water on it to see if there's any leaks. In terms of the FEA, which next slide, these are not the most recent ones. Our PDM went down, so I couldn't pull up the most recent test, but this was prior to adding a couple of weight saving features. As you can see, very blue all across the board, so it should be good in terms of that. Finally, in terms of timeline, we just have, once we get this part manufactured, we're hoping to do it in the next week or so. We're going to start running our tests in sequence there. So is there any questions? Yes.
For when you're doing your seal test and just using water, are you gonna apply any pressure to it? To the seal itself to make sure that
under higher pressure?
Exactly. Like the expected pressure plus whatever factor of safety you want to tie in.
I don't know if that was integrated into the plan for that, but yeah, that would actually make a lot of sense to add some pressure to that. I think we might have been assuming that just because of the weight of the water that might have similar effects, but I think we'll have to figure out how much pressure we need in the Nosecone injection test to get an accurate amount of pressure for the seal test. Any other questions? Yes.
What's your fixturing condition for your FDA?
So the fixturing conditions, we said it was the radials there, and then I just did the forces from one side.
Have you looked into like the deformation around the seal?
Deformation around the seal in terms of how that would affect the
Yeah,
like the quality
like
of
with
the seal.
with the strain, more like deformation be big enough to counter.
Well, I'm
Yeah, so it's the loads are only gonna be applied after the seal uses purpose. Loads are only gonna be applied after no score eject, so it's not sealed anymore.
Okay, that makes sense.
yeah. So there you go. Yes.
Follow up to the FDA question, what parameter or unit are we looking at? What is the scale here?
So we're looking at 1,005 newtons in terms of the drogue deployment, and then about 2,000 newtons of force on the main deployment.
But what are we looking at here is the stress?
Oh yes, this is stress test.
Okay,
yeah.
what is the scale here? How close are we to failure?
We're pretty far from failure from all of the stuff. There was on the inside, so for example here, on the inside of the radial screw here, there was a little bit of a red area because it's a lot of stress directly near those screws. But even then, it wasn't even close to like red or failure, so.
Okay.
Those numbers that you mentioned, were those dynamic load numbers?
I got those numbers from Tim.
You did a case statically, right? That wasn't, that's just standard FDA.
Yeah, I did.
So, those are the highest loads, in doing perfect deployment. But the FDAs were done statically.
Okay, yeah. So. Is there anything else? Yep.
And just complete unfamiliarity with this.
Yes.
I see with two altimeters and two black powder cups, I assume if one fails, the other one, like
Yeah.
everything will still do with it.
Yeah, so the way that the release pins work actually, so if you think of it like this, there's a tether that runs between the two release pins.
Okay.
So, and then the drogue chute is linked in like that, right? So if one of the pins releases and it slips through, if both of them release, awesome, that should work. And ideally in terms of pressure, yeah, if one goes, then should pressurize it further. Yes.
Following up on that with the black powder cups, so obviously it's going to be designed so that if one of them goes, it pressurizes it and ejects the nose cone. But then if both of them go, will that be like too much pressure? I know we've had issues in the past with rockets where like the upper fuselage is just like buckled out under that pressure.
So those were repeated tests and we kind of used those fuselages. We never had that problem during flight. Just a single, it's just a single deployment event, if you will.
Okay.
The general concept is that you test with one cup until you get a minimum amount. Like you're very confident in a minimum amount, and then you test with both cups and make sure nothing gets damaged, and then you just follow that.
Okay.
Yes.
Is there any mechanism to retain the pins prior to ignition of the black powder? Or are they just kind of slid in place and?
So yeah, there's the shear pins there that should hold it in place, but those little black
Oh, I see.
things there that the pins go in and then there's a little. Perfect. Yes.
Now, I think I asked this at the last meeting. You guys have used this specific deployment method many times, right?
Yes.
It's always been successful.
Yes, yeah, to my knowledge, there was the previous times there was issues with entangling. But in terms of the actual deployment of the main, it's always worked. Yeah. Yes.
What's your O-ring group sealing out against?
So that's gonna be sealing against the fuselage. Yeah, because there's gonna be the fuselage of the ring should cover that. Yes.
I'm sure you'll go over this in the parachute section, but is there a mechanism that prevents the shock cords from shooting out from the black powder cups? That was an issue in a previous rocket where the pressure from the black powder shot up.
Like shot out the vein.
The shock cords prematurely. The shock cords themselves. Is there anything that
I
prevents
have
them from being
not
shot?
looked into that actually, so I think we're generally, so it's gonna be bagged. So in terms of the parachute, so that there's. You also.
I'll look into that.
Yeah,
No, that's not something I had considered. That happened to us at the point. No, that's not what happened to anyone.
Yeah.
Alright.
Yeah, there are photos. Anyway,
So yeah, we could look into that. And yes,
What's the reason for having the eye bolt not centered in the bulkhead?
I think it's because of stresses. I know that we were planning on going with a radial hole design or for the pins. It would be kind of facing inwards before, so we had to move it back. But also with these, since it's hollow on the inside there, if we have a bit more spacing from those, we're hoping that it will put less strain on there and have less chance of ripping out. I think was the idea. It's more so just having it distance out a little bit, because we ideally don't want it to. Yes.
Sounds like a valid point there. In your stress analysis, did you have it fixtured only based on the holes, like the radial holes?
Yeah, we did only have it fixtured on the radial holes.
And you looked at the aluminum stresses, but did you look into the carbon fiber stresses based on those screws?
Like the stresses on the bulkhead or on the fuselage?
Yeah.
I don't think we did actually. I think we were thinking of doing a zip ring test.
That'll be under the fuselage section.
Right, fuselage section? Yeah. But you took the numbers from his and put it in the fuselage?
Yeah.
Okay, cool.
Yes.
Did you also fix the whole length of the fastener hole or just the edges? So when you did the fixturing on the plate, did you use the entire thread hole?
Yes.
On the outside? Okay, so then that entire hole can't move, when in actuality it should be able to sort of flex, right?
Yes.
Okay.
How is the eye bolt spec? Because I know last year we just had like very big eye bolts that had like a factor of safety of like 10 or 15. How is the eye bolt spec this year?
I think the eyebolt was spec on how much stress it could take.
Okay.
So we were expecting 2,000-ish newtons, and that has, I think, like twice.
Okay.
That, so. Anything else? Yes.
Twice that in working load or twice that in failure load?
I think twice that in failure. I might be mistaken on that, but I'm quite certain it was twice the failure. And also in terms of the maximum loads, it's not gonna be doing those maximum loads for a long amount of time. If I'm not mistaken, it's just gonna be once it deploys, it's gonna shock. So if it's twice the failure for a quarter of a second, if that I think that's pretty safe. Thank you.
Everyone, I'm Tim, parachutes here. So this is the general outline of the parachutes during ascent from the cover bulkhead to the Nosecone. Not much has changed for the parachute design since the PBR. We're still applying hemispherical. Geometries with a coefficient of drag of 1.3. The drogue was sized using our parachute sizing spreadsheet. The boards were according to SolidWorks, and they're now exported as DXF files. They're laser cut, and then laser cut stencil will be used to cut the nylon boards for manufacturing. The main, since we don't have resources to justify making or buying a new main chute this year, we're just going to use Zinnia 2's main. It's same profile. It's going to slow down the rocket by 1 meter per second. after both deployments, the parachutes are gonna look as shown in the diagram here. The assembly of the parachutes will be done outside of the rocket, which will flank the main, and since the drogue is smaller, and the packing job is less complex, we just fold them into quarters. They will then be wrapped in Nomex bags along with the shock cords. They'll be folded in zigzags and secured with painter's tape. They will be attached to the recovery bulkhead, and all of them will be inserted into the rockets as one piece. The main integration points is obviously the recovery bulkhead and the Nosecone bulkhead with quick links and eye bolts, and also the tackling tether. Here's us plating the main in completion last year. Some of the tests, critical ones, the main parachutes for our test two rockets have a tangled after deployment. So to avoid that, we're going to be, we have done and we're going to be continuing with our main deployment tests where we just pack everything and then pull the parachute out. Drilling tear out is just the shred lines will be made out of 550 pound paracord, and they'll be attached to the canopy using a triple zigzag stitch. We are going to be using a PTM machine and a tensile testing machine to pull those apart to see the calculated factor of safety. Older samples have shown a factor of safety around 270 newtons for this year's drogue size, and since we're using black powder for Nosecone ejection, we're going to be kind of coordinating with Nosecone ejection tests and using the Nomex bags, packing them with nylon straps, see if any of the nylon is burnt. When we get to a point where we can eject the Nosecone without burning any of the nylon, we will be actually starting testing with actual parachute.
Just a quick question about the nylon, Nomex bags. Are you guys manufacturing your own Nomex bags, or is it off shelf?
It's where we're manufacturing. Oh, yeah. So this is our timeline. As mentioned before, the main is already we're using one already existing main, so this is all largely done. Next slide, please. The drogue design is mostly done. We need to still recently do spectral bridle and do the tensile tests with the shroud lines to make sure our single triple zigzag stitch holds. And then we're going to start manufacturing and testing. Next slide, please. And it's that timeline for yes.
So I know you were talking about the making sure we don't burn the nylon on the black powder. In terms of the actual test, are we going to test the forces, like the air force on is there any way to test the air force on the parachute to see if there's any chance that it's going to damage during that deployment? So are we going to test the loads on parachute?
Loads on the parachute. That's a little difficult to test. We don't have enough wind tunnel to just deploy a parachute, obviously. So what the club has done in the past is just use a car that risks damaging the parachute, just like rubbing up against the ground, and also we need to go rather fast on a very straight line with the deployed parachute that you can't exactly just put on the road. We can do that, but currently not planning on it, but that's obviously an option. So we're gonna, since we know all the forces, well not all the forces, but so we know the main forces acting on the parachute and the weak points being the the stitches, we can do smaller test articles to ensure factors, good factors of safety on the individual components of the parachute instead of testing the whole thing.
Okay, so we would also use a similar method to the shroud line tear out.
Yeah.
That,
Yeah.
yeah, I was also just, actually,
Do the deployment tests test like the deployment of the parachute at the speed that we're expecting them to be slowed down?
No.
Does the speeds that they're pulled out at affect the risk of them getting tangled?
I wouldn't think so. It's a sustained pulling force, and also during descent there will be a lot of wind rushing up and trying to catch the parachute to inflate it. Whereas when we were pulling it, it's just kind of lumpily hanging downwards. My assumption would be that if anything, deployment of those speeds would make it less likely to fail. But there's a good way of building it up.
The Nomex bag that's gonna be hosting the parachute, I know to some extent that with the previous Xenia tube, the bag played some effect in not allowing the main to deploy just because part of the string got wrapped around.
That was yes, but also that string isn't like a part of the bag. That was something extra that we had added. And yes, we're not gonna have any loose strings near the shroud this time.
I know that when it comes to parachute packing and rigging, small imperfections can have a big difference, but since the previous two rockets had a tangling issue for the main, are you trying a different approach or are you changing?
Very much similar again, but the flaking method that's like pretty much new. Well, not entirely, but that's pretty much new, and we're doing repeated ground tests to make sure nothing gets tangled up. But yeah, that's something we can do. Yes.
And for folding the parachute, do you have like a procedural document of how to fold it so it gets folded exactly the same every time, or is it kind of depending on who's folding it?
Well, the fabric is quite malleable, so it's always going to be a little different, but the procedure is recorded as a video. Actually, a judge in Launch Canada, Michelle Wonders, who unfortunately couldn't make it here, but like we did the other as well, taught us how to do it. The geometry of the parachute itself kind of, not course corrects, but the geometry of the parachute itself is used as a datum. So you lay flat on a table and then you use the cores as reference points to fold it properly, basically. So yes, but obviously since it's fabric, everything's gonna move around a little bit depending on who's backing. Okay. Sorry, it's friend.
For somebody else asked a question about the actual loading on the parachute from the aerodynamic forces when it opens.
Yes.
In the last review thing that I was part of, I mentioned the idea of a slider for slowing down the actual opening of the parachute. Was that considered further?
No, but that is a very good idea.
It could tangle lines too, so like it'd be something to.
But it's definitely worth looking into. But the way we fold, actually, put in, and this is obviously not the same thing, but that deployment speed is something we consider. We put in 45-degree folds at the very bottom so that the parachute doesn't deploy, doesn't inflate as fast as it otherwise would.
Yeah, I was just wondering when you're testing the fabric and stitching the lines and so on, are you planning on steady state loads or the natural when it first comes in? When you set your maximum forces there, is that what you're expecting when it's actually working, or is that what you're expecting when it snatches in?
Those are the deployment loads. So those are samples, yeah, but we unfortunately can't simulate those because of the tensile testing machines work quite slowly.
I guess that's what I was wondering when you test it. Like, you know yourself, if you try to tear a piece of fabric, if you just tear it and you're measuring the force in the machine, that's one force, it'll have a certain maximum it takes to tear it. But if you rip it, it's different. So I'm just wondering when you do your testing, can you simulate that ripping attempt that your rocket is trying to do to the parachute?
You could try things with weights. There's definitely things we can. There's definitely important looking into. currently can't think of anything we can do to do that consistently, but go ahead.
I don't know if it's like necessarily consistent, but do you like
Tie
tie
a master, yeah, that's why.
tie a mask, just drop it and
yeah,
just be
that's-
like,
That's what I thought too, but that's almost like elegant testing methods, and also the forces are decently high, so you don't just wanna be like dumping down 20-30 kilos of like whatever steel on the floor, some would consider that a bad idea. But yeah, we do them very slow static loading. But the mass is an option, and if we think of some other way to do shock loads effectively and safely, we'll definitely try that as well. So we have those questions. Yeah.
Are we expecting similar loads as previous years?
Yes, it's the dryness of the rocket is actually quite similar to both CM and CM2.
Okay, so then we've tested that.
Yeah, the drone we've tested it looks like alright.
What is the max diameter of the parachute?
7.4 meters for the main, sorry, max diameter. That is, I do not know that off the top of my head.
Whatever 27.7 is that in meters? Hoping.
27.7. Oh, sorry, those are inches. That is one gore of the drone. Yeah, that's just the drone.
So for the main, it was.
I don't know that off the top of my head. I can. We can pull it up. What is the?
Is it about 4 meters? The diameter?
Like, yeah, about 4 meters. So like a 2 meter radius, 4 meter diameter. Yeah.
Okay. I'm just asking because I'm considering like what type of drop towers might be around here available to you guys.
Oh, I mean, it would be very nice, but I highly doubt we can just chuck a main with like 15 kilos dangling from it down like a building, unfortunately. So that's, I mean, it's
into the grass, who cares?
A little man on the bottom, and on the 1st of April, and you call it an inch.
You smoke so much over edge break that you would.
I don't know if this is like worth the effort it would take, but you could have like kind of like just two things like on a rail system with like it's spring loaded, and you could just like press a button and it just goes really fast.
For a short period of time. I mean,
I don't know if that's like at all worth it, but
that is a lot of machining or a lot of buying for not a lot of results out of everything.
Yeah.
Yeah. Especially for a main, that would be difficult, but it's a good idea. Yes.
My boss at my last co-op, he paraglides and he floated the idea of potentially dropping stuff for us if you want to. Floated the idea. So we can talk later.
That sure, yeah, that would be wonderful. Hopefully, with this talk and everything against any other question. Yeah.
Hello, everyone. My name is Marvin. I am in charge of the Nosecone manufacturing. It is the main aerodynamic surface that will get in contact with the air at our supersonic flight. So the design, the overall length of the nose cone, including the integrated coupler, which will all be one part, is 28 inches with a mass of 1.2 kilograms. And the coupler length is 5 inches. That's the length that will go into the fuselage. Since the PDR, we have added a telemetry system in the nose cone. That is our backup commercial off-the-shelf telemetry system, which has prompted a couple of material changes, which include changing to fiberglass instead of carbon fiber for RF transparency, as well as changing the tip from aluminum to leaded steel to add some extra weight for increased flight stability. The key design requirements that we're trying to achieve here is to have a defect-free aerodynamic surface with perfect concentricity and symmetry, as well as minimizing drag during supersonic flight, which is obviously the design itself, as well as mounting and integrating flush while being sealing so that the recovery system can deploy it. And also mounting concentric trucks. To manufacture, we are going to manufacture the metal parts in-house at the UVic machine shop. And we will be manufacturing the composites in-house with our student developed methods with in-house pre-preg curing ovens. I won't get into the details here now. To assemble the nose cone, the tip is held on with a single plate that is also leaded steel and a 2-inch commercial off-the-shelf bolt. It'll be simply clamped in order to for everything to be able to move and shift as it heats up during flight. If there happen to be any significant temperature changes, which aren't which we don't expect. And in terms of the bulkhead, we just have the eye bolt with a jam nut and a couple of seal screws to hold the telemetry system in place. To test, we're doing a couple of tests, but have a small scale model here. So the main concern we have is buckling due to aerodynamic pressure, as approximately 60% of the aerodynamic load is within the first 2 inches of the rocket. This is a rough estimate. So we want to make sure that there's no buckling. So we'll be doing a vertical buckling test. We'll be doing a tear-out test to make sure that the shear screws, that the radial holes are strong enough and we won't get tear out as the nose cone deploys and gets held back by the tether. As well as we wanted to just heat up the tip to see that nothing deforms too much, to create some misalignments on the tip, as well as just adding a bending moment to the top of the nose cone, just in case there's any off-axis aerodynamic loading. We want to make sure that it can withstand those as well. Make it nice and rigid. Go on. So now we'll get into the fuselage, which is the second main aerodynamic surface, or I guess, yeah, the second main aerodynamic surface besides the fins that will come in contact with the air. So the total fuselage will be 99 inches long and is consistent of two main sections coupled with a coupler that will be bonded into the lower fuselage. We have a test fuselage here. This one here is 48 inches long, so that will give you some reference. It's closer to the upper fuselage, although it is made of carbon fiber, the same that the lower fuselage will be. The total mass of the upper and lower fuselage is approximately just over 4 kilograms. It will be made of, like I said, carbon fiber for the lower, and to get RF transparency, the upper fuselage will be made out of fiberglass. And similar to the nose cone, we make sure that everything has no defects and portrays good concentricity, as well as passing all the bending, buckling, and shearing tests. Go on to the next. So to manufacture, we will be using in-house composite manufacturing, which includes rolling onto an aluminum mandrel, using a pre-preg, carbon fiber, and a wet layup fiberglass layup. I've just included a small diagram here of how we roll our fibers in order to get a 0, 45, 90 layup to make sure that we have strength in different directions along the length of the fibers. And so to assemble is it's a quite easy process. We complete the composite work. We bond the coupler to the lower fuselage using structural adhesive for composites, and then it just gets slid together with a tight fit. there's actually a section of a coupler in here as well. So that's how that will be done. And in terms of completed testing, we have had this fuselage in particular on a compressive testing machine. We've applied 5,000 newtons, and which gave us approximately a factor of safety of 1.9. Obviously, it was non-destructive. We might be doing some further tests in the future to see how far we can push this, but we've got great plans for this fuselage on its own. So it survived a bending moment of 666 Newton meters. Yeah, so that the 3-point bend test is completed. And in terms of future tests, we are planning on doing the tear-out testing that Brandon brought up earlier to make sure that none of the radial screws will be able to zipper through the fuselage, as we've had happen in testing in the past. We'll be doing some compressive load to make sure that the pressure from the engine doesn't damage our fibers, our fuselage, as well as having a shear test that will ensure that we don't have shear failure as well. And then, of course, the dynamic test that we were talking about earlier, that will be that now we have a plan for of actually testing. So does anybody have any questions about the fuselage or Nosecone?
For the Nosecone, can you go back to like the transparent view?
I think it was one of the earlier slides. One more?
Yeah. So, are we looking into the length of the antenna? Like, is it in up? Because I just see like it's quite offset from the center. Do you reckon that length?
That's something, but we'll have to check. Maybe we'll put it in the minutes. Make sure that the telemetry can tell us how much space that Big Red B telemetry system requires. Yep.
For the coupler, are we planning on doing any tests with the coupler, like bonded to a fuselage to test if that's the failure point?
Yeah, so all these tests will actually be completed on fuselage itself, and then we'll also have two sections with the coupler in the middle, and we'll be completing the bend test as well. Although we need lower, there's a lower calculated bending moment on the coupler itself. If you go back to the side of the graph. I think it was later. It was the first testing slide. One more. There it is. So you can see that the maximum bending moment is loop. So you can see it's right here on the lower fuselage, and the coupler sits right here. So there's a significantly lower bending moment. So it doesn't have to be quite the same strength. And Adam?
I have two questions. First one for fuselage, I guess, because we're here. How did you push on fuselage during the testing?
How do we haven't completed, oh, it's for the bending moment?
Yeah, the test bending. How did you apply the pressure or the force to the fuselage?
We had two lower supports that were 21 inches apart, and we had bulkheads in at those points. And then we applied pressure in the middle, also on a bulkhead, so that we were measuring pure bending instead of the shear, or instead of getting shear or buckling, right?
With like a pretty fine point, or was it kind of a smooth surface?
It was a smooth surface, and then we were applying it directly to the bulkhead. So we were hoping to get the purest bending that we could.
Okay, and then for the Nosecone, why is it so pointy?
It showed in the calculations that it would be that's the most desired for supersonic flight, especially as we're getting into the low twos of Mach 2. The plan is to have the tip of the Nosecone approximately as sharp as a center punch, so it wouldn't be sharp so that you could cut yourself, but it would still be significantly pointy.
Based on our readings and research, based on like the AIAA missile design guide textbook, that was the optimal profile we decided for this, like this profile of flight and the speed ranges we go through. was this like 3/4 profile parabolic series. So that was what we decided.
So I just comment, because I remember when I was researching the profiles, the blunting at the front, you know, for small blunting up in front, it can be, you know, not too impactful for the drag, but the other side is the complexity of making a fine point perfectly during manufacturing and how to set that up, especially for something long that'll sort of gyrate as it's manufactured. But, yeah.
So the for manufacturing, this is actually a previous prototype. This is approximately how big it will be. During manufacturing, we'll actually have it'll be on a 1-inch fixturing. There'll be a 1-inch diameter fixturing cylinder. So then it'll be turned down that way. So I don't think it's too long, but Rodney ensured me that it can be done. So
Yeah.
I have full confidence.
I was just gonna ask about whether you're planning on doing the manufacturing in-house, how you're planning on doing, are you doing it all with a single point tool?
I'm not entirely sure, but we did speak to Rodney about it, and he said that he could help us again to manufacture this part.
Rodney's probably the maker.
Oh, yeah, you're fine.
Like, because he made that one, and he's like, yeah, I can.
I went to speak to him, and he said, yeah, I could help you again. So
Yeah.
we are in good hands. Yes.
I know we talked separately on Discord, but through ANSYS, were you able to get any, does it give you any of those static or stagnation pressures, or what kind of forces you're dealing aerodynamically on those depths of the different profiles?
We've had some trouble with ANSYS, but
yeah, so
Gordon might be able to speak on it.
So we have been fighting like the license server for quite a while. Actually, it's over a month, but it's running now. But the way how we spec like temperature and pressure is based on like the easiest one, aka stagnation condition. So that gives us like back the top, like the worst case, because it would be like it would be fully stored.
What number did you get for that?
I think temperature is around 100 something degrees. But we have also done like steam calculation, and it shows it will warm up like a 50 degrees. Yeah.
Was that at the 1.7 mark?
Oh, it's an iteration throughout the whole flight.
Oh, is that the small motor or the big motor?
The small motor.
Yeah, I think the maximum temperature that will be experienced, like the air temperature, is about 150 Celsius, which I don't like. The entire flight up to apogee is exactly how long?
Flight up to apogee is like 39 seconds.
Yeah, and so this is a machined.
I'm not worried about the aluminum specifically in this case, because you've got the tip there.
Yeah, exactly.
But the other surfaces, like you mentioned, the holes and the fins, I don't believe are protected on their leading edge, are they?
Very true, yeah. No, in terms of like having metal to protect it,
Yeah,
no, it's a pure cover.
I remember the calculations I gave you, I think we came up with,
It's a
how sure are we that 2.3 Mach is the maximum?
Pretty sure at this point. I'd say like 2.5 is like the absolute ceiling. It'll go definitely no past.
Because as you go up in those numbers, like even slightly, we're talking between, you know, if you manage to get to Mach 2.7, which I think was your original before you added weight.
Yeah. Before we strengthened the fuselage, to make sure that we have everything, this added a little bit of weight, so that took out our, took down our.
I did rough calculations and came up with temperatures as high as 400 Celsius. If you manage to get up there.
We'll definitely make sure to put more time into the temperature, especially on the radial holes, right?
Yeah, and the leading edge of the fins too, I don't know. No.
Okay.
It may be worth.
That's great. If somebody can think that in a minute.
Simple cap over it and just.
There's no such thing as simple cap.
Sorry, wrong word. I'm gonna just do a thing, right? Yeah.
Any other questions about manufacturing or? Yes.
For your radial holes, how are you cutting them?
We actually have a filament winder that we built in house. It's essentially a 3-axis machine. So we have a sled that can move along the X axis, and it can plunge. and it can also hold a cylinder and rotate it, so it's essentially a CNC specifically for drilling and manufacturing fuselages.
Well, what I mean is like, cause when you're like, say on your pressure bulkheads that have the screws going through, how are those holes getting cut?
Oh, 3x CNC, no.
Yeah, it's essentially, it essentially is like, if you picture this, we can rotate the cylinder, and then we have a drill bit sled that can move in this direction and plunge directly into it. We'll be using carbon fiber specific drill bits.
Okay.
For that, nice short and stubby that actually have the centering drill as part of the drill, and we'll be doing a really slow operation.
And then are you treating those edges at all afterwards?
No, not as far as we know right now. I don't know if we'll be deburring them even, we'll probably, because they, the radial screws should sit fairly flush in those. Yeah.
I haven't heard you mention the transition from subsonic to supersonic. We've talked about the early part subsonic, we've talked about the big number supersonic, but is there any implication of that actual, you mentioned earlier, sonic boom? Is there anything we need to consider at that actual moment of going through the sound barrier that showed up in the sound?
I'm not too sure, maybe Matthew, if we have you done any analysis on the actual sonic boom? As far as I know, those are very difficult calculations.
That's why I.
The pressure, yeah, the pressure.
Yeah, I think
the transition.
As far as I'm aware, like, we've not been asked those like questions from the people at competition. I think from what we've been told, like, unless I'm mistaken, a lot of the concerns around breaking that barrier is like vibrations and that kind of thing. And we've discussed this with like the launch counter people, and they said vibrations were not as big of a concern, and there was something we could look into if we wanted to. But they said generally it's not too big of a concern because we accelerate so fast, we go very, very quickly past that region. Yeah.
Deceleration side, how long are you spending in that region?
I don't know off the top of my head, but I can bring that up right now. I can get back to you on that.
Are there any implications with coming back from supersonic flight to subsonic? Probably not.
I like, as opposed, like, would the forces on the airframe be different, you mean? Like,
Wait, you're speaking about like after max, like
after max Q, yes, you're now in deceleration, you're gonna be in the transonic range, obviously longer than you would in the acceleration part of the flight.
Yes, yeah.
With the vibrations and the and you're not sure where exactly that's going to be. It's temperature and pressure for the day will very much determine that.
Yes.
You know,
We'll look into that.
It's
For sure.
worth
Let's
looking
look
into
into, yeah, we'll look into the max loading a bit more for the deceleration. In a minute as well, if somebody could. Jackie?
What's your, have you guys considered like how vibrations will affect your onboard electronics and like connections between subsystems?
I personally don't know of any, but that's a great question for the for the electronics.
Launch Canada said not to do it because it was too complex. Like, if the solder joints, it's not worth doing it, is what they said, basically.
But I mean, like on your wiring harnesses and stuff like that, because that can cause chafing and that sort of thing.
I think they said if we could find a shake table, that was like the closest thing that they could get to that. But I don't know if we have that.
Okay.
Yeah, I hadn't thought of like any like something shape or something, but yeah, and then but the connectors themselves, we did spec ones that have like clips and stuff. So like the connector side, I was thought about that a little bit, but yeah, like no, like yeah, nothing.
I think it would be worth putting some tests for that into the plan as well.
Have you guys ever had any issues with your carbon fiber delaminating?
Not as far as I know. You mean as a result of the pressure, or?
Yeah, because you're saying that you didn't do any post-processing of the holes once you drilled them. I would just be concerned at passing the sonic barrier, delaminating your carbon fiber if you haven't treated your radial holes, edges.
Yeah, so the edge, if you, there'll be a screw in there.
What kind of screws are you using?
We're using, well, we're just using set screws. Like, they
Like
do
what
have,
kind of
they, sorry?
What kind of cap?
No cap.
Oh,
Just they
yeah.
actually, they're in the bulkhead, and when we slide it in, and then we back them out from the bulkhead.
Okay.
Yeah, there's no cap on them. But yeah, that's definitely something to look into, is if we could make that carbon fiber any stronger, to make sure that there's no delamination when we do have that aerodynamic pressure in the radial holes. Although I think the screw will help us.
Yeah.
But it's definitely worth
I didn't
looking
realize
into.
you guys had screws in the back mount. I like that idea.
All good? Thank you.
Hello, Liam, doing the fins this year round. It's okay. Here's. As far as design goes, I think we have some rocketry alumni here. Probably is going to look really familiar. There's a kind of a reason for that. We kind of try not to reinvent the fin, as it were, for this rocket, just because we're trying to get basically our kind of first supersonic, successful supersonic flight. And ever since we switched to basically a design similar to this on every rocket, it's been a very, very strong design. Had a lot of punishment dealt to it, and it's always kind of come through, including crash landings and the fins themselves being basically unscathed. As far as weight goes, it's going to be 4 pounds or 1.82 kilograms. Basically, the geometry of the actual fin itself is kind of constantly being refined, and those themselves are going to be made out of just the 1/4-inch carbon fiber plate that we purchase. Since the CER, we have kind of switched from actually, this is kind of the old one from one of the HIAC series. It's kind of got it's like a single design, it's not split. Since the CER, we've actually kind of switched to a 2-piece design, just for mostly mass saving, with kind of spacers in the center to kind of keep its basically keep its distance, so you can have the screw holes be consistent for easy installation. As far as the requirements, it's going to have just basically it must interface with the fuselage without any air gaps, because that's kind of like a big unknown. We wouldn't know really what happens if the air gets underneath the features, so we just kind of want to avoid that entirely. And then they have to have an accurate locating features, so we want all the fins to be as close as possible to a nice pattern around, just so you have consistent lift no matter where the rocket rolls to. Those are specifically the spacers. Just kind of a comment on that is the more and more I machine myself, the kind of more and more I think that that's going to be really hard to make. So one of the things that actually I'll bring that up in the testing. We'll keep going for now. Next slide. Basically, as far as the how it's going to be made as well, these are going to be carbon fiber posts. This is the fin cage. Basically, this is the interface inside the fuselage. Basically, we're just going to have simple rings with radial holes connected with the carbon fiber posts, just for easier installation. So you just slide it in, and then these interface with that, and that's all it interfaces with. as far as manufacturing goes, it's just gonna be mostly aluminum. We just have always had really good luck with that material. It's kind of, and as far as the fin feet themselves go, we've never found that the aluminum has given us any kind of, like, it's like never failed under like any load that we've ever put it under for this kind of purpose. Yeah, the for manufacturing, obviously like this kind of thing is probably it's very difficult to make, but I have kind of a preliminary workflow that I think will allow us to, yes, you know.
Where were those ones made?
These ones were made at Rainhouse. So the idea, okay, so that actually is going to be, that's kind of a backup plan. Is if we can't get a good result, we are going to just outsource it again. But currently I'm like decently confident that we can do it in-house. So that's kind of the major thing with the fins right now, is kind of going into a prototyping phase where I'm just going to manufacture with probably Julian's help the entire fin feet out of plastic, just so we can mill really fast. Just go and confirm the workflow, and then also kind of verify whether we're actually going to even go with the spacer design, because currently the spacers have pockets on the inside of the feet, recessed pockets, and that's really hard to do consistently with you have mirrored on both sides. So I'm going to manufacture it so I have the pockets, but also there's another idea where we just use shoulder screws to kind of shoulder screws instead, which will basically do the same purpose, and it'll be a lot easier to do.
We can talk about the specifics of that later.
Yes.
We can talk about stuff like hat spaces as well. One of my main concerns, you were talking about not wanting to get airflow under that.
Yeah, I have
getting that surface correct. It's extremely difficult.
Yes, so we're actually not going to rely on the surface being perfect. One of the tests that I'm going to actually, you can go to the test. I don't know if it's the next one. Basically one of the tests is we're going to try using gaskets, basically just a thin layer in between. And the way we're going to kind of test to see if we can get a good seal is, I was talking to Gordon about like basically using ink and a vacuum bag, and just like evacuating all the air out, and then basically taking off and see if there's any ink underneath. Because it should replace all the air with ink if it's not a good seal.
Yep.
But yeah, like we already tested actually manufacturing the radius, and while it is like decently good, it's not perfect. So we're gonna try to account for that as well. You want to go back. As far as assembly, I kind of went over it already. If we go with the spacers, you kind of just insert the spacers into the fins, and then you put the fins, the feet on the fins. You screw it in. These are number 6 screws. And then you put it on the fuselage. The fuselage itself will have relatively large clearance holes, so there shouldn't be any like issues with the holes not being aligned, and they'll go directly into the fin cage, which is underneath. And basically it will just be held with the screws themselves here, and then also a lot of tension and friction to hold it in place as well. So you can have those two things helping it stay in place. And then as far as testing that goes, we'll probably end up doing the same kind of zipper test with the recovery bulkhead on these as well, just to make sure that it's not just going to fall off the bottom by just kind of shearing through.
Yeah, so if you don't have shoulder screws like connecting the two fin feet, there's nothing, as far as I can tell, there's nothing planting them, like actually planting them together. Are you confident that they're going, like the fins are actually going to be planted in place strong enough that those spacers are going to hold?
Oh yeah, so the idea is that it would be clamped. It's clamped at the top from the springs, sort of screws here, And then it would be clamped from the bottom from the fact that like it's going to be interfacing with like the rings as well. So all of those should be basically with those two things, the fins themselves should stay in place. And also the shoulder screw idea is not to have the shoulders go all the way through, because then that takes away the clamping force from the fin, but just like partially away for locating purposes to lock it in place. Yeah.
What's the purpose of the posts in the assembly?
So actually that came up in the last review. The idea is that we could remove them and then install each ring individually. But that would be kind of just really annoying to assemble. And the carbon fiber posts themselves are just so light that it was kind of determined that it was worth it to have those as a spacers for basically just for installation purposes.
Is there a concern as well? Because obviously I get that side of the installation, but is there concern as well of like it being similar to the post and plate design from last year, where you've got your radial holes and they don't necessarily line up with where the posts are in there, and nothing lines up when you're kind of struggling to get screws?
So if that were to be the case, very worst case scenario, the posts could be removed and you can still use the rings.
Okay.
This is just like we're trying to get it like to be a good alignment this time, and one of the things we're going to try to do is have this manufactured well in advance so we can actually put it all together and detect any issues. Because if we have it manufactured beforehand, like if we have the fin feet and the fins manufactured beforehand, if we have any issues with like nominal sock size of like the thickness, we can actually just make the rings to spec of what we actually physically have instead, and we should have way less issues with the screw spacing. I forget who was first.
Okay. Specifically for that's since we're looking to assemble here and then ship the rocket as a whole anyways, we could literally assemble everything first, and then like it would be annoying whether we only have to do it once. Remove, because there's set screws holding the posts together, right?
Yeah,
just remove the set screws and just pick them apart from within the fuselage. It would be annoying as hell, though. We have a Victoria and then we can just ship it as one piece.
Yeah.
And then breaks. You don't want to do anything else.
I'm also like I want to see if we can, if it's possible to actually have the club ship the feet and the fins like already attached here as one piece, because then we can basically make sure that what we like make is going to fit together once it gets to comp as well. Yeah.
And just remind me, I think I asked this question last time. Has the team had a supersonic rocket where the fins stay attached to the majority of the rocket in supersonic flight?
Yes.
Yes.
Yes. Yeah. And that was done using this method.
Yes.
And what
I
was
think it was actually this rocket. This one we took off. Pretty sure.
The fins survived, but I remember, was it just the bottom portion that it was attached to, or was it the whole rocket? I don't know. I was not. Because the fins are the part I'm most worried about in the transonic range, especially with that sharp kind of change in angle at the front.
Is it like the force or the heat you're concerned about?
So there's something called a critical Mach number that's not Mach 1. Are you familiar with that concept?
Not personally, no.
Okay. So what happens is certain parts of an airfoil, especially when there's discontinuities in the profile, such as a sharp edge or a changed angle, you end up with localized supersonic flow along the surface of the airfoil. You end up with various shock waves and parts of the actual airfoil that effectively are stalled and no longer effective at those speeds. So what you can end up with, is the effective area of your fin being dramatically increased for a short period of flight, which would put you into negative stability. So, or very, very violent oscillating. And that's, I think, where, don't know. Elizabeth. That's, I think, where Elizabeth was asking about the transonic range.
Yeah.
My default is to avoid too much of that by just making sure there are no, like, everything is pointy as hell, and
nice continuous profiles after that point, because it minimizes the risks in transonic flight. I guess, did we look into making that leading edge sharper and more continuous?
Leading edge of like the actual fin itself or
Or you're
the,
touching, well, I don't really care about the bases, they're not, they're aluminum and they're
yeah,
not the main part.
of like the fins itself. Well, basically, I mean, like the fin itself, like the geometry is kind of more generated from analysis. I don't think we've actually really like
that part right there is the part
this part right here.
Yeah.
Kind of Gordon manufactured them last time. Do you think it's possible to get like a sharper, basically just like a sharper edge?
So not just sharper, but a more constant profile.
Oh, just more constant profile. Okay, then that would be like, yeah, in his domain.
Yeah, so basically what happened was we had fins in the past, which were that like perfect diamond profile where it comes down, it's the diamond, and then it just immediately comes back down like that. There's no flat edges on the sides. But they were 3D printed, and then there was carbon fiber was put on top of them, and that was the rocket the fins pull out of.
Yeah.
So we decided to change manufacturing methods, and we went to these fins.
Yeah.
Which were used for the supersonic rocket, which the fins stayed on the part that we found. But that what you're saying in terms of what happened with there was a failure and a couple of due to bending, but I think that might be what you're saying, of at some point in the flight, we may have gone into negative stability with that fin design, and then too much bending, couple of breaks.
Possibly, I don't know, I haven't seen all the pictures, that's the only part of that rocket I've seen, so. Yeah. I don't know.
Okay, so that's something we should definitely look into moving forward. So yeah, I'd definitely be interested to talk to you about that afterwards.
So the sharpness will be limited by what your wind is, because we will not be sending it. Sending is just like it's very easy to make it out of tolerance. So this year we're aiming to use like a chamber, so that will be limiting how sharp.
Yeah. And also he was saying leading edge as well, which is like, I guess like the steepness of this angle, right?
I don't think that'll matter too much.
Okay. I believe
It changed what speed that this all happens at, so the more this way it is, the more perpendicular to the rocket that leading edge is, the sooner these problems would occur in the flight. So I wasn't as worried at Mach 1.7 because that angle is actually below the angle, the shock angle for Mach 1.7. Where it's very close, but at Mach 2.2, I don't think you're below that angle, so you know, that will also play the factor.
Well, definitely something to look into for sure. Noah?
Yeah, so is it a part of like what you're saying with like the integration and assembly? A part of that plan for testing it, will we be testing the integration of the motor casing as well? Because I mean, you were in competition with us and we had severe issues there. So is there a plan to significantly before have the fuselage, have the fin gauge, have the motor casing, and check once everything is locked in?
So yes, that can will be tested, but the idea with this design is actually the rings themselves won't be touching the motor casing at all. Like they're not designed to be a locating feature for the motor, so we shouldn't be able to run into that issue because they'll actually be like a decent amount of clearance between the rings and the actual motor itself. Yes.
Has there been a detailed analysis on the screws holding these fins on and shear and pull out?
So, oh sorry, go ahead.
I was just because it looks like those are pretty small and there's a ton of thread engagement and there's also thin threads that's receiving the threads.
So there's the only thing I've done so far is kind of like more basic hand calcs for just like the lift to make sure that it doesn't like shear this way. As far as like actual analysis on that, we were kind of like hoping to get like some better numbers from the ANSYS, but if that fails, when I actually have like a prototype and thing in hand, I was planning on basically stress testing the actual fin itself, using I believe like mostly weights to just like make sure that it can't like shear, like basically like I could even do like a stress test of failure and just
Yes.
seeing when that happens.
But that might not tell you anything. I guess what I'm getting at, do you know what sort of stresses are pulling, like what sort of drag is pulling the fins down in a way, and also bending them out and pulling the screws out? And is that significant enough to sort of, shear fin off during flight?
As far as I know, I don't know if we have like a drag number for that yet.
No,
'Cause that's
need to-
basically still something that we have to get a simulation for. That's why that's one of the reasons why the actual fin profile themselves is constantly kind of being optimized, because as we get new information, we're going to be changing this, and the entire actually CAD itself kind of automatically updates around the fin profile. Yeah, so kind of we're going off the idea that like a bad simulation is worse than no simulation, and just kind of designing with the idea that we will refine it as we go. Like can always make the screws bigger if we find that they aren't like adequate, but they have like a relatively, at least for like the lift and things like that, that we're going to experience, like the safety factor is kind of ridiculous, for at least that portion. That's kind of the only data I have right now to work off of.
I wouldn't be concerned. I would be a lot more concerned about the shear than the lift in that case.
Yeah.
Because in lift, you're putting those in tensile, and for most screws, you can assume your shear is about half. What I would suggest doing, once you get your pressure on the wing from your drag, find your center of pressure, locate that moment, you'll get your bending, you'll get your shear, and then from that, calculate your shear flow on your fasteners, and then just do the number of fasteners or size of fastener per shear flow. If you take it into 220, you can do that.
I haven't, but the idea is that once we actually get more solid numbers, we are going to do all that kind of analysis on the fins, and that is going to be part of it. But we just unfortunately don't have those numbers right now.
Yeah. There's also the shear from the inertia because of the heavy fins during launch, so you'll have to also think about weight.
Yeah. And I think that is something that at least we can get like a general number, like the mass of the fins will be changing because like when they change geometry, the mass will change, but I can probably get like a bulk part estimate on that like pretty soon after this.
I mean, we'll be pulling about 30 Gs, so
yeah,
it's a fairly simple
yeah.
calculation.
Yes.
If I've understood correctly, your fins are held in the three places with the rings effectively as your backing plates, is that right? Or they're acting like washers?
Yeah, like
they should stay back, like that's what's actually fastening it into the rocket.
Yeah, exactly. They're basically tensioning. This is tensioning. The fin feet are tensioning against this on the fuselage. So it's just like compressing into the fuselage using the rings. Yeah.
And so I guess one question that I wanted you not necessarily to answer, but to consider going forward is what's the rigidity of that whole business? Because you've got larger holes through your fuselage and the actual fixing of it, if I could say that, is your screws going through your feet and then into your backing. If that is going to be, if there's any play in that at all, or if your ring is not thick enough, or this is what some of the others have been pointing at, if you don't have enough threads, that's where that's not going to be as strong as perhaps.
Yeah, and this is something that we can test. We're planning on having the like from experience before, like the interior, the inner diameter is actually like more consistent than the outer diameter on our fuselages. And part of the process for making the rings was going to be turning them down on a lathe. So the diameters like should be pretty, like the fits should be pretty good. And like they should be spaced enough that, and the fuselage itself is incredibly rigid. Like if you actually hit the two materials together, they kind of like vibrate like rocks, that like kind of like sound like neodymium magnets if you've ever kind of, so that it's like, so it's kind of, it's crazy rigid, and I think with like those two things, that shouldn't be super issue, but again, we'll kind of like, there's always ways to make it more rigid.
I think what people are bringing up as a concern isn't that each disc itself will have issues, it's about the freedom together.
Yeah.
This is like you talked about last year's was post and plate design. This year you've got your carbon fiber rods. The reason, I'm assuming the reason you're doing that is so you get parallelism between each and you get cylindricity as your result of that, if you're talking GD&T. I would very much try to get those as parallel as possible. That is how you'll be able to get rid of any inconsistencies. And as far as manufacturing is concerned, that means making those carbon fiber rods really, really to spec, more so than your actual discs themselves. The discs aren't difficult. Your rods are actually the part that you need to get to a very tight tolerance and be very straight.
If you're only clamping part as the thread, then you could put compliance and flexural features inside of the ring so that it can flex and move out towards the inside diameter of the fuselage. Still get all the clamping force where you need it. But I don't know how helpful, you know, the rest of the ring is going to be on the screws, you know, in between with the fins. So you could have some flexure design in there so the rings can expand.
Oh, okay, so you mean like making the rings like slightly bigger than the outer diameter, so they kind of like
Well, not
compress?
necessarily bigger, but so that
Like
when
a collar.
when you thread all the way around, you can sort of suck up against the fuselage and get some better clamping.
So this is very similar to what I brought up in the first one, because in the first meeting we had, the fuselage was not nearly as stiff. So I was suggesting making the rings stiffer, the exact opposite, because I wanted the rings to be the support structure and the fuselage to bend into the ring. In this case, now the fuselage is so much stronger. Your design there where it actually bends out away from the screw threaded holes probably is actually better now, because it will allow some of that flexure to provide the clamping force. As far as the rods being the constraining factor there, I think your fins themselves will be the vertical constraint for parallelism.
Yeah, that was, I think that was kind of the idea, was like even without the like the rods, like the
fins themselves,
the fins
act like the
themselves
rods, but on the exoskeleton.
are like these are all like very defined like distances, but if people have more manufacturing experience and think that that is not enough as a constraint.
I think it's enough as long as you have enough hole depth in there and you've got a tight enough clearance hole. So if you've got a clearance hole that's too wide or you don't have enough hole depth in that, your screws
Oh yeah, the idea is going to be this is going to be a tight clearance, but the clearance hole, the actual fuselage is bigger, just to make sure that that's not a conflicting issue. So it's just hole and hole.
Yeah, that sounds good.
Have you considered the galvanic reaction between the aluminum and the carbon fiber?
No. Remind me what that.
Well, because basically what happens is the carbon fiber will eat away at the aluminum. And over time, you're gonna have corrosion issues. Because I know generally, like in aviation, if you're putting aluminum next to carbon fiber, you put a layer of fiberglass over top of the carbon fiber, so it doesn't eat the aluminum.
What is the time scale on this? Like,
It depends on how long you're planning on this rocket on the rocket lasting. If it's like you want one launch and no more, less of a concern. But that's hence my question.
yeah, I believe like that's like unless we're kind of have a different plan. Like the idea is that this is going to launch once and then it's going to go into like a display.
Then yeah, it's less of a concern for sure.
The I don't think we're planning on relaunching this one. Yes.
So with this, I know you talked about using a gasketing material of some sort.
Yeah.
That would significantly mitigate or completely eliminate this, stops oxygen from getting in there. So as long as that works, then it shouldn't.
Yeah, well, there's gonna be a gasket in between the fuselage and this, but like this, carbon fiber plate doesn't have a gasket, or at least like we can.
You're gonna seal that though, right?
Yeah, this one, this one, this one's gonna be a gasket, this one is going to be like an actual, like a compound, like sealed compound, so yeah, I guess you're right, it won't be touching.
As long as no oxygen gets in there, the effect of that is.
I just wanted to float, we were talking about, the gasket idea is actually fairly new between the fins and the fuselage. And we were considering, like engine head gasket material. For its like rigidity and its ability to seal under pressure. I just wanted to float that in the room if anybody has any objections to that. Because it's actually like the perfect material for gasket.
I think it's good material for it. It's what we use, or what the IC team uses, but my only concern for that is your leading edge, like all the way up at the front there, is pretty far away from any clamping fasteners. So I don't know how much clamping force you're gonna get right at the tip there where it matters most.
Yeah, that's really.
Because you've got
that is a good
at least
point,
a couple inches there away from the nearest fasteners.
Yeah.
You're not gonna actually get that much clamping force on that tip where it matters most.
Yeah, we probably would have figured that out as soon as we did our vacuum testing.
Yeah, is there like a possibility that we can we might be consider like a hybrid approach of like using the gasket for most of it, but then just like sealing the leading edge with the same material?
No, I think we'd have to get more clamping down on the tip. I think that's what we have to look into, is how we can get the tip to get fasteners closer to the leading edge.
Before you guys start about complicating this design, can I ask why you're so steadfast on moving away from the old design?
The old design of what?
Up to 10 feet.
This?
Yeah.
It's actually relatively similar. I mean, as far as.
You mean 2-piece versus 1-piece? The thing about
Oh,
that
2-piece versus
is-
1-piece, you mean, or?
2-piece versus 1-piece, and that itself, when you get Rainhouse to do that part, they can ensure that profile extremely well. Rainhouse is a tier 1 manufacturer. We're not here, and yes, I like the idea of vacuum testing of ink. That's a really good idea of how to do that, but you're still giving yourself more unknowns doing it that way than you're kind of like old reliable. I like doing new design and stuff like that, but I wouldn't throw away your old design just yet.
You mean old reliable isn't like just like have Rainhouse do it again, or just use
Potentially.
Well, yeah, that's like that's something that we're going to be validating pretty shortly.
Okay.
Like I'm going to, like I said, I'm going to manufacture, or at least manufacture it here, and then basically test it on like our fuselage, and see like how good we can get, and also like test to see how like good the surface finish is, and basically everything, and whether it is possible to do it in-house or not.
Right,
And then we still should have enough time to like get Rainhouse to make it if that doesn't work out.
Yeah, you said you're planning on prototyping plastics. Is that just for the workflow, or is that?
That's for the workflow.
Okay.
Yeah, the idea is like once we get the workflow down, because I don't want to like spend money on aluminum if I don't have to, like if I just mess up. Once I have the workflow down, we want to make an aluminum one pretty quick after that, so I can actually start doing like physical tests on it.
Sounds good.
Yeah.
Sorry, the fins are very important, obviously, so I wanna ask a lot of questions, especially aerodynamically on these. What altitude is your max Q at? About between 5,000 and 10,000 feet, my guess is.
Altitude for max Q, I can bring that up, yeah. Oh. Pause.
Well, assuming it's in that range. You know, at Mach 1 point or Mach 2.2, you're dealing with a couple hundred PSI, potentially a couple hundred PSI of air force on that leading edges. So right at that tip.
Yeah.
You're going to have air trying to get underneath that fin with, you know, definitely over 100 PSI, maybe as high as 2. As a gasket material, like you were planning on using an actual sheet gasket material, not a liquid gasket.
Yeah, we're floating.
We were going to test it to see if
Yeah.
that's like
Just like
a
you can
possibility.
buy big sheets of the head gasket material and laser cut it to the perfect shape, and then.
I don't think it'll get perfect enough. There's my instinct there is I think you will have a hard time.
You put gasket.
like some sort of liquid gasket that stays semi-rubber, and then, you know, after it's attached to the rocket, maybe cutting it back with a knife or smearing it smooth around the outside edges.
Yes. We've used stuff like that in the past for the other rockets as well, so.
Yeah,
shouldn't be
it's
too foreign.
keeping that air out from underneath that, all those surfaces is going to be
Really important.
non-trivial.
I agree, because like, it's not really, don't really know what happens, like, there could be any number of things that could happen as a result of
Are
that.
you guys allowed to use liquid gasket material to cover over the bolt holes and counter cores and stuff that have screws in them? So you won't be able to access the screws anymore or anything like that, but you could smooth over the surface of those bolt holes once you've actually put the things in.
That is actually a really good idea, because. Yeah, that actually something I didn't consider is, cause like the idea is you want them assembled. And then like, they'll just be like basically treated as one piece once they're assembled. So unassembling them is not gonna be like a huge deal, so we could fill in these and kind of shape it, so.
I would suggest that.
Yeah, that's actually a really good idea.
If you don't need to disassemble them, if you need to disassemble them, don't do that.
The idea is we don't want to.
We don't have to, we can consider one assembly a competition, and I don't think we have to disassemble it.
Yeah, because then you can look at, instead of like just a liquid gasket, you can look at something like a structural adhesive.
Yeah, exactly.
And then bond those things down, then the clamping issue becomes less of a worry because it's a structural adhesive. And if you're slightly off on your radius, it also is less of an issue.
There was more hands.
I was just gonna suggest it's something like RTV or something, you could put underneath, clamp it down, and then, you know, once it's cured, you can just trim it off, and then you have you know, liquid gasket that is also compliant, so if you take it apart, you can, you know, you probably wouldn't want to use it again, good, I guess, and it's not super permanent.
I think we get that name down if that's possible. Okay, cool. Yes.
Okay, really good feedback. I think for the sake of time, we should move on to the next section. We have a lot to cover.
Yeah.
Unless there's any.
I didn't think there was any more.
My question was along the same lines, I had my hand up, but it was.
Oh, sorry, I didn't see. I
Yeah, so
apologize.
you use it, so you already used it. But that was the hand in the back.
Oh, sorry, I didn't see it. Really apologize for that. But yeah, we're all good. Cool.
Thank you for the great discussion on things.
Most important.
Yeah. I'm glad you spent lots of time on it.
All right, hello everyone. I'm Ryan and I worked on the motor integration for the Soyuz rocket. So just a general overview of the design. There's kind of two parts to this. So at the bottom, you have the structural component, which is the thrust crown. And that's composed of the thrust crown and the retaining ring. And then at the top, you have a centering ring to make sure that the motor's axis is very aligned with the rocket. And then this is just a section view of the very bottom part here, because that's the thrust crown at the bottom, and then the retaining ring at the top. And this is just a section view that shows kind of how we're transferring the thrust. So the motor has like a shoulder there, and we're basically just clamping onto that shoulder, and that's how we're transferring thrust from the motor to the vehicle. So since the past CDR, one piece of feedback I received was that these sets of radio holes were way too low, and we were kind of worried about like the tear out of the lower fuselage as a failure mode. So in order to fix that, what I did was I raised the radio holes up 3/8 of an inch, and then I also incorporated these radial weight saving pockets to the design. Next slide. The three kind of load cases I just want to talk about that kind of drove the design. The first one is the thrust load from the motor onto that thrust crown. And then the second, the other two load cases that I've been considering are the inertia from the dry motor, like the dry mass of the motor onto the retaining ring when the recovery drogue and main deploy, because that will induce high acceleration on the vehicle as well. I haven't really been considering the load case of impact. I'm kind of assuming that the boat tail is going to take a lot of the impact force, just because that is very hard to kind of characterize. And I'm not really worried about like the safety effects of that component failing when it touches the ground. Next slide. Yeah, so in terms of analysis, that's something I've done a lot better of a job at, and improved since the past CDR. Going into the first CDR, I just used a static load assumption with a very high safety factor, just because of the uncertainty of treating it as a static load. But since we've kind of switched the motor, I've looked into a better analysis method. So the biggest, so what I chose to do is I chose to use the modal superposition transient analysis, and I used that in ANSYS. And basically you can use, you can look at the vibrations of the part, and you can look at the natural frequencies and mode shapes. And that allows you to characterize the dynamic response of the structure from those transient loads. So instead of just looking at the maximum thrust from the thrust curve, I imported the thrust curve and I analyzed the whole load with respect to time. And in ANSYS, basically what I did was I set up the modal solver, and then that output is the setup for the transient structural solver, as well as the load curves. So the equation of motion really that kind of uses the transient solver. It is basically I neglected the damping of the part. I'm assuming that the energy in the system in the thrust crown is conserved, and that is a conservative overestimate. And I kind of chose to neglect the damping because what I saw was the material didn't, like, the part didn't deform too much in the analysis that I ran. And I basically assumed that most of the damping of the part would be like from material deformation. And since it was so small, I'm neglecting that. So that'll be a conservative overestimate, which I think is beneficial here. And then for the failure criteria I used for like safety factors and stuff, I use von Mises. Next slide. So this is just a screenshot of my analysis, but basically how this is the thrust load case on the thrust crown. So you have your this is the plot of minimum and maximum and average stress over time. The maximum stress is 8.52 pascals, which gives a minimum safety factor roughly 3.2. And then next slide. The retaining ring, I didn't simulate the drogue deployment case just because the overall magnitude of the thrust curve was much lower than the main. So I'm kind of assuming, since if the part can handle the the load from the main chute deploying, it'll survive the drogue. And then this part had a much higher safety factor than the other one, so that was good to see. Next slide. So in terms of manufacturing, all these parts use 6061 aluminum. It's economical, strong, and lightweight, and very machinable, which is very useful for this design. And then I just want to highlight that I'm using 632 screws to kind of to bolt the retaining ring onto the bottom of the truss crown. And I just chose a coarser thread. This is something I'll touch on a bit more later, but I think the coarse thread will help with the screw tear up failure mode. And then for the centering ring and retaining ring specifically, those those parts are designed to be machined top down on a 3-axis mill in-house. For the kind of wavy weight saving cutout on the retaining ring, I'm planning on using a ball nose for that. And then for the thrust crown, that part, the radial pockets, we're gonna have to send those out, but I'm planning on doing as many of the features as I can in-house. So I'm planning on turning down the outer profile and then putting those bottom holes in-house. Then I'll probably send that part out with a fixture plate to an out-of-house manufacturer, and then they'll do the radial holes and the radial weight saving pockets, as well as like the wavy weight saving cutout on the top of the part. Next slide. And then in terms of assembly and integration, these parts they mount to the lower fuselage, and then your truss crown, it also integrates with the boat tail. And as Liam discussed, that the fin cage, that's not pictured here, but that does not interact with this assembly at all. And it's also important to note that that these two parts are the mounts of the rocket's launch slugs. So there's one on the thrust crown and one on the centering ring. Next slide. Awesome. So in terms of testing, I did a FMEA analysis of like all the failure modes in the scope of flight before touchdown of this assembly. And the two failure modes, or two of the main failure modes that I identified, these are probably going to end up being the same test, but we don't we don't have a super good idea of how the composites are gonna behave. So we just wanna test the radial, like the tear out and the failure mode to see which is gonna fail first, the lower fuselage or the screws. There's an old Mech 446 report in the drive that says that the screws are likely to fail before the composites, but that was done a while ago. So obviously there's a bit of uncertainty there, so we're just gonna double check that with the test. And we'll figure out the load, we'll figure out the load that the assembly fails under, whether that's the fuselage or the thrust, like the screws. And then from there, we'll determine if the design meets the criteria or not. The next slide. The other thing that we want to test as well is we want to test the tear out strength of the 632 screws. So that's also going to be a tear out test. And the other thing as well that I forgot to mention with the previous ones as well, but I'm going to be looking into, I haven't figured out exactly how to calculate an equivalent static load for this yet, but that's what I'm planning to use, find like an equivalent static load. And then I would like to do kind of like a tensile test with this assembly. And then the other thing that we should test, maybe not as formal of a test, but we should test the design, like the concentricity of the motor, and that it allows the motor to be concentric, especially because this design with the centering ring, it's new to the team. So I just want to make sure that, just because there's a bit of uncertainty there, I just want to make sure that that'll work. Next slide. And then in terms of timeline, I'm planning to kind of finalize the analysis and just make sure that all my assumptions are well documented and that everything checks out. I should have put write testing plans as well here, so I'll get to doing that, writing those testing plans and getting the procedures for those. And then I want to be manufacturing prototypes and testing before the end of this term. And then I also want to get the flight hardware because I'm planning on going on call for the summer, so I just want to finish this project before I potentially leave. Next slide. Do you guys have any questions?
I have one question about, can you go back like a couple more slides? There. So on the crown that we're pointing, the crown piece?
The first crown is up.
Yeah. So the material between the radial holes, what function is that serving? Because all the load is going to be axial, right?
This.
But yeah, so between, because you have the radial, like the weight saving cut out, right? What's the material above that doing?
Oh, that's that is transferring the force from the motor to the thrust crown. Because if you go back to the slide with the ANSYS simulation of that part, what I found was that I mean, I probably could look into potentially weight savings there because like the edge is quite blue. Like if you're referring to that edge.
Yeah, that bridge there, just because all the loading is axial, right?
Yeah, but I just figured in terms of manufacturing, I just thought that that might be like putting like a chamfer or anything on that. Like that might be kind of more difficult, more expensive than it's worth. Like I don't know if you can get.
I'm just curious if we need it, right? Like could it be? If
yeah, he's saying if you like completely remove the bridge.
you just have like the material rises up to where the radial holes are, and then it's more like the centering ring that you have with the wavy top row
round shape. Like
oh, sorry, I see.
Make it so the holes are at the points of
so the whole
triangles.
Yeah, the whole locations would stay, but then it just like tapers down to save weight instead of having a hole cut through.
We can potentially do that. I was just a bit hesitant. The screenshot doesn't really show it well, so my apologies, but I found that there were pretty high stress concentrations like in the radii pockets. And they were pretty distributed along the pocket, so I was just a bit hesitant to kind of take material out from there. But I could definitely look into that. Yeah, can you guys add that to the Paul?
I'm not sure where your load is starting to act on this. You've got stress concentrations at the top of those bridges in your pictures. Where actually are you loading this part in your simulation?
Oh, sorry. Can you go back to like the first slide of this? The back one. Yeah. So basically, I'm loading it kind of on the shoulder. From like the load is being applied from the yellow shoulder of the motor onto this like edge.
Yeah, so you can't get rid of those bridges because that's actually where the force is applied. Because the yellow is the engine, right?
Yeah, the yellow is the shoulder.
So you're using those to clamp down. Okay. Other question. This might just be a geometrical one, but why aren't the radial holes centered between the slots.
Yes, that's because you have these screws here. So like the screws take out part of this.
Okay.
And then you have your radials.
Yeah, that makes sense.
Martin.
Yeah, I just wanted to say like, well, to that, maybe just to clarify, like you have, if you go back to the, just one of the more detailed, yeah, so the fuselage sits on the outside of this, and then the engine is kind of on the inside of it, pressing on that edge that's hanging over. So really, I don't think you could get rid of that, those cutouts, because that's where the force is applied from the engine. And then something else I wanted to say was, as the fuselage bends, your thrust will be off axis. So in your simulations, have you ever run a simulation where you load one side more than the other?
No, I haven't. I've been assuming equal distribution of load. I could definitely.
I think we should definitely look into seeing if the thrust will be off axis, how that will affect the thrust rate.
Yeah, why would the thrust be off axis?
Just with bending and everything, like, because the if you go back to the slide that has the entire motor in it, because you have the retaining ring about halfway, but I would never assume that it's perfectly aligned. I would just see a case where
So
it's
do
not.
you mean off axis and coming out at a vector angle, or do you mean off axis as in the center of the motor is not actually centered in the motor?
Just that the thrust is not perfectly aligned with the axis of the, like the central axis of the rocket. Like just ever so slightly, but I don't know how it reacts. It's just
And do you apply that ring by sliding it over the rocket motor to the bottom then?
Yes.
Okay. So there's no other point on the rocket motor that's as wide as that.
No,
it's kind of designed as well.
If we can go take a look, or if you can see it from here, do you have a radius on, like, what is the radius on the inside of that shoulder that's holding it down?
At the inside of the
So you've got the shoulder that's clamping down on the motor there. Yeah, right there. Move your finger up slightly.
Oh, this one.
Yeah.
That one's gonna be the locating feature.
I know. What is the radius on that?
I think that's about.
Or is it
It's
a-
98 millimeters, so it's 3.8 inches.
No, I don't mean the radius.
It's like a
of-
fillet.
So you're gonna have, if you have a 90-degree corner there, you're gonna have an insane stress concentration. You should do that. If you're gonna mill it yourself, do that with a bull nose at least. I'm wondering, what is your like radius in CAD under that corner? Yeah, where you're clamping onto your motor, because you don't have a radius there, you're gonna have an insane stress concentration.
The radius, I think it is a quarter inch. It might be more, like this radius in here, like.
No. I'll come point at things.
Oh, yeah.
Come point at things, because this is really important to me.
I think that is
I imagine there's zero radius in the design.
This, right there, that corner of the motor, is gonna have that corner. Your actual clamp that you have under this is gonna have that there. It needs a radius of some kind. Like, it'll be a small one. We have bullnose cutters in the shop that have like a 30 thou radius, but you're gonna want a radius and do your stress constant calculations with that radius. Because you should do hand calcs with this with a stress concentration in there.
You did
Yes,
your,
that's the notice. Thank you. Yeah,
you did your finite element analysis with no radius there, correct?
yeah, I did with no radius.
And did it show a little red spot in those corners?
No, I didn't. But that could be FEA
Could be
matching.
not a finite
Yeah,
element.
so I think that's really good.
But you're doing this with 6061 aluminum?
Yeah.
It does have a fair bit of yield, which will reduce that stress concentrator. It may not be a problem, but it's worth considering.
Julian?
If you add a radius in there, is that gonna affect where the motor sits against that corner?
I think it should be fine. It would just decrease the contact area. But
is the motor perfect 90? Is the other question. Because the
No,
motor.
the retaining ring have like a small radius, but that's something that we should look into is like how big is the radius on the commercial off-the-shelf ring, and then we can determine how big we can add a fillet on there without interfering like anything. Yeah.
And then, actually, I have a few questions, for you guys. In terms of manufacturing, I was planning on doing the wavy features. I was planning on that being sent out to a 5-axis. Kind of the assumption around that is that, the part could be kind of rotated and then, spun, and the end mill will just kind of move in and out. But just from like a CNC programming perspective, like, is that a very hard thing to program, or like, are there better ways to do that, wasting pocket?
Because you don't actually care about the top surface of that. There's no reason you can't do that on the 3-axis mill that you're doing, and just accept that the profile of the cutter will be engraved into the top of that surface. If you're okay with accepting that, you know, lack of tolerance, then you can do it all on one. Same shape.
I was just, I just didn't really want to do it in-house, because I've heard from people who like use the rotary, head that we have here, that it's a bit, I don't know, like it's a bit.
Slop.
Yeah, it's a bit sloppy, so
You don't need to, the slots, you need a rotary head for, and the slots you can go in 4-axis, Ringhouse could do those nicely for you. The actual top profile, since it's not a making profile like what he was talking about, that you could do with a ball nose on a 3-axis.
That's
you know, like the slots are actually something that requires a 4-axis more than what that surfacing on the top requires. And if you make your radii nice on the top, you can do it pretty easily with tools we have in shop. But if you set it to a nice nominal radius, you could do it with a ball nose and not have to worry about the tool path looking too ugly. The actual slots would be what you want a 4-axis for. But Ringhouse could do that really easily.
Sounds good. Can you guys add that to the notes, like consider ball notes for that? Maybe. And I think those pockets are probably like the most, like we get the biggest weight savings from like those radial pockets. Yeah.
Could you make those holes instead, like instead of having linear slots, increase the number of them and make them all individual holes? Because I imagine that would overall decrease the weight more, because you get away with thinner. Like a slot, when it's being pulled apart, really concentrates the forces of the ends. Whereas if you have a bunch of holes, the bridges between the holes would reduce the bending force and concentrations at the end of the slot.
Yeah, I can definitely look into that. But I also found that like from the FEA analysis, like you still have a decent safety factor without material there. So I just figured it might be more efficient to just like mill that out like as a solid pocket than to have like multiple holes. I mean, it probably wouldn't be that much more efficient, but yeah, I mean, I can look into that.
I think what he's saying is you could get larger diameter than what the slot is there.
Oh,
larger
I
diameter holes, more of them spaced out. You could probably get more efficient weight savings with holes.
I'll look into that. Yeah. Can you guys add that to the meeting notes?
Yep.
And it's one machine of them.
Yeah, it is. That we could probably do with this. With the holes.
Yeah, because then we just get like a fix.
Yeah, the same way you guys do your radio holes.
All right, I think that's everything. Thank you guys.
Great, thanks, Brian.
All right, so I'm Alex. I'm going to be talking about the boat tail, which is this little piece right here. Oh, good. So in terms of mass, it's pretty light. It's a pretty small part, and changes since the PDR. We've finalized the profile and optimized supersonic flight. So the design requirements that this fills is to reduce drag and flow separation in the supersonic flight and absorb the impact load when it hits the ground. So in terms of manufacturing, it's no major changes since the PDR, and it's very similar to how we're manufacturing the Nosecone. So a female mold will do the layup with pre-pregnant carbon fiber. The female mold will be made of MDF and that'll be machined in-house. The aluminum retaining ring, which same retaining ring as Ryan just talked about, that will be made in-house as well. So we've selected carbon fiber because it's good thermal properties and it's fairly lightweight, and aluminum is also inexpensive and pretty light relatively. So in terms of assembly, this is the same diagram as for motor integration. So we've got the number 6 screws going up through the carbon fiber part to the retaining ring, going into the thrust ring there. So same as before. So in terms of testing, we're gonna be testing for mechanical failure as well as thermal failure. So mechanical failure when it impacts the ground. The point of the part is to absorb the load, so we're not really concerned if it sustains a little bit of damage. But really what we'd be concerned about is if it gets absolutely crushed. So we expect loads of about 3.8 kilonewtons with a factor of safety of 1.5, we get about 5.7 kilonewtons. And yeah, we will test that on the MTI machine for compression. And then in terms of thermal, the boat tail would actually be directly exposed to the exhaust. But what we don't want is for the boat tail to soften so much that it can't absorb the impact load. So we would expect the carbon fiber to start bleeding at 500 degrees Celsius, and the epoxy resin is supposed to withstand up to 177 degrees Celsius. The exhaust temperatures are expected to be somewhere between 1400 and 2000 degrees Celsius, but the motor only burns for 3 seconds, which is not nearly enough time for heat transfer to attain either of these two failure temperatures. So we may still do a propane torch test, which will simulate temperatures of 1960 degrees Celsius. Yeah. So we can skip this, it's not, yeah. And now we will take some questions. Gordon?
Can you go back to the CAD?
Yes.
Maybe one more. Yeah, this one. I see there's a stack. Like, yeah, at the mating surface of the ring and Bulkhead. I go up. Yes, exactly. Go right. Yes. So would you make it like 6 flush? Is it CAD?
I think it is just a CAD thing, yeah.
Okay. Okay. Another question is, so if you go back to the load, so maybe like, yeah, this one. So for the forces, that like the average impulse load?
Yeah, so this is, yeah, the average impulse load.
So it's not necessarily like the max impulse.
No.
Have we looked into like how we do a proper drop test maybe? Like rather than expected actual load, because I assume it would be higher than that because that's the average.
Yeah, we have thought about a drop test, and that is a reasonable thing we could do if we ran some calculations and we'd only have to drop it from like 1.5 meters with the balance of mass. Matthew?
Going back to what Gordon was talking about with the step, is like, I noticed there's not a picture of it in here, but in the overall design, it's like there's the fuselage, then there's a step down to the upper part, like the crown. So there's a step down to the outer part of that crown.
Okay.
Then there's another step down to the retaining ring. Then there's another step down to the boat tail. And I think just the concern at the moment is that is almost certainly going to cause some form of flow separation. And we don't know the impact that's going to have on stability. So I think that's something we definitely need to look into for the boat tail profile overall, but especially for those transitions. I think those need to be made smoothly, because if the flow separates already by the time it reaches the boat tail, then the boat tail is not going to be doing much.
Yeah, okay. So what I believe, I thought that these were the same diameter here. I was pretty sure of that, but yeah, it could be different, but we will look into that. Okay. I believe, yeah, go ahead.
So the taper on the back of that boat tail, what lock is that designed to separate that? For the flow separation?
Unsure. I would not look into that. Yeah, it's something we need to look into, because the boat tail is mostly for well, the impression I got from reading some research was that it was mostly subsonic, it helps with stability, and then supersonic, it's not as sort of effective. So I've not looked into the flow separation, but that is something I need to do.
Yeah, correct. It definitely is much less effective at supersonic, but the reason why I asked is because again, this is one of those transonic problems. In this case, this would occur in the high supersonic range. But if you pass a certain Mach, you're gonna end up with no flow touching that. And the risk there is again a stability issue where you get a wind gust and you end up with flow contacting one side of the boat tail and flow never merging on the other side of the boat tail. The pressures would be so low, I don't know that it'd be a problem.
Yeah.
But it'd be better if you could just avoid flow separation altogether.
I think that's something like I need to start working on overall, is looking at like the more supersonic side of things, because right now Gordon's doing all the ANSYS side of the aerodynamics. I'm doing like the open rocket side of the aerodynamics, because not particularly accurate, but it gives a good overall picture. So I think what overall needs to happen is I'd quite like to hand off the open rocket side and start helping Gordon with like actually identifying what's going on with the supersonic flow, and then moving forward from there. I think that's what needs to happen over the next.
It looks, since you brought up this slide, again, that was easier because I can do the math really quickly. Looks like it probably wouldn't separate us. A 0.5 inch difference from top to bottom, and it's 1.5 inches tall. Correct?
Yeah, 1.55 inches tall here.
And it's only a 0.5 inch difference between the radiuses.
Yeah.
Here,
Should be good to mount 3.
Okay, cool.
Makes it easy.
all right. Thank you.
Could you go to the slide with the failure analysis or the failure points of the heat, the temperature stuff?
Yeah.
Okay, awesome. Yeah, so logically, of course, 3 seconds isn't long enough to cause a heat transfer of 1400 degrees Celsius. That's not enough time. And I don't know if this would be important, but maybe look into, okay, with that 3 seconds of burn time, what would the heat transfer possibly look like? Because we have to think the rocket, it isn't going perfectly straight on, right? And neither will there be like zero wind or anything like that. So based on like how it's going, whether there's wind and stuff, I don't know how that would affect the exhaust and heat coming out. But just because of the arc of the rocket and everything else happening, you could get instances where the exhaust is like more concentrated to one side of the boat or something, causing heat transfer. And it's probably not a big deal, but if the epoxy can only withstand up to 177 degrees Celsius, it is a lot less than your 1400. So maybe just see if 3 seconds of direct contact would melt something. I'm not sure.
Yeah, so the exhaust actually doesn't contact the boat tail. The boat tail sits flush with the end of the motor here. Okay. So unless the exhaust goes up, there's not really much, like there's not much contact between the exhaust and the parts.
Yeah, I wasn't gonna get into this because you're right, because the boat tail is ahead of the end of the rocket. I would almost leave your argument at that.
Yeah.
Because a propane torch as a test methodology, that's my understanding.
Yeah,
Like,
it's just not here.
mass flow rates mean a lot to heat transfer, and although there may be the same physical temperature,
right?
A propane torch's mass flow rate is, and the density of the gases are not even on the same order of magnitude as the rocket engine, so it's not a good test. I know since it's going a lot together, I might even just take that out. Like,
yeah, okay,
you know,
yeah, fair enough. Yeah, just to see if the epoxy melts.
Yeah, but how long are you gonna leave it there?
Well, just to see how it reacts, because I don't think we have actually tried to melt epoxy.
Yeah.
Like, and if we hold the propane torch to it for 3 seconds, like just in one little spot, and the epoxy looks fine, then we know there's nothing.
Yeah,
But
not really. No, that's what I'm saying.
Right.
So the logic behind that, the science behind that is flawed, unless you were to hook a
Oh, you're talking about yes,
air
of course,
compressor up
flow
to the
rate.
propane torch and run the flow at the same rate.
I know what you mean, yeah.
You're getting the same temperature for the same time, but you're not getting the same density in heat transfer.
Yeah, Q isn't the same.
Yeah,
So
exactly.
we're fairly confident on this part, and Q dot, yeah. And that the testing may not even yield anything useful, just for covering all our bases.
So I'll tell you a really interesting anecdotal story. If it's funny for you. 2 seconds.
What do you think, your time? Okay, sure, why not?
So my friend and I built a potato cannon. And I don't know if any of you burnt your eyebrows off by lighting like butane on fire and like, it doesn't really hurt your skin. I will tell you that we had a tiny pinhole from where we drilled the screw beforehand. We decided it wasn't necessary. Well, my friend put his arm over that and fired the potato cannon. In less than like 1/10 of a second, he had a pretty good burn hole in his arm. So that speed of the gas matters a lot for heat transfer. There you go.
Thank you. Yeah. Do you have any other questions? Yes. More like,
Okay.
do you think is the exhaust would be having a philosophy way greater than what we are applying, so we would not have that much convection, so with radiation.
Yeah, the radiation would be the only thing I'd worry. There's no way the exhaust gas is turning around.
Yeah, exactly.
Because it would reduce the rocket's efficiency, and it's already super like the exhaust gases are well into the supersonic range.
Yeah,
and they couldn't physically turn around.
Anything else? No, then I guess we're going into the intermission. So we've got coffee, hopefully it's still warm in the back there, and donuts. So enjoy. Yeah. Listen. There are certain things that you learn when you guys expect.
All right, thank you, everyone. We'll continue with the avionics.
For those who don't know, I'm Mateo. I'm the electrical lead this year, and the project lead for the plug computer. And the other name, Isla, she's also worked on a lot of the schematics and stuff, which is not here today. So an overview of the flight computer, it is essentially just a data recorder and also a controller for payload. So it has to record data and sensor values, store them, as well as monitor the temperature of the payload that will be talked about later and trigger a motor at a certain point in flight. And then it also sends data to our custom antenna, SRAD, Student Research and Development. I'm not sure if that's been said in this presentation yet. And yeah, and so the assembly you see on the right, which we'll be talking about more in the next section, is one of those PCBs on the top is the flight computer. Another one is for string gauge. And then yes. And yeah, so that's one other thing. And the other requirement is the 24 hours battery life to account for time on the pad, time during flight, and to account for a general recovery time, make sure it has power to monitor the temperature of payload until we recover the rocket. So 24 hours, which kind of picked as a general window. If we're recovering the next day, there's going to be other complications. Anyway, okay, and then next slide. All right, so the general design and what's shown on the slides is kind of like a wiring diagram. It doesn't show up fantastically on the screen right now, but the general idea is like you have the flight computer PCB. It'll be connected to some batteries, and this shows 4 batteries. We are considering reducing to 2 because we don't need all 4 batteries from the main calculations. It has 4 connections to the payload, as well as just USB power to some cameras that were shown in the diagram in the past, and then it also connects to SRAD telemetry controlling it, strain gauges system, and yeah, and then those are some wiring diagrams, some of like the Raven boards that we're talking about in the recovery section, and the telemetry that's in the Nosecone as well. Yeah, so these are the schematics of the core of the system. We've selected an STM32 that is based on the requirements we have, the number of ports, and we're applying from free octahs, so that's enough memory to have all that firmware on it, as well as it has two IMUs for low acceleration, high acceleration. The low one is for it has a maximum of 16 Gs with
Our rocket now expecting to go up to upwards of 30. We've also added a higher acceleration one. And previously we also had a higher acceleration one that was spec for 2 energies. And I think we're gonna go with that same one, but possibly reducing it to 100 Gs, so I put 100 Gs on here. I don't think we're expecting anywhere near 100 Gs. I hope. And then, yeah, and then one pressure and temperature for monitoring the internal temperature of the rocket, it's around the payload, as well as debugging, database programming, and power ports and connections for USB for offloading data. So the data that's recorded is stored on a flash chip that's on the PCB itself, and then after the flight, we'll plug in a USB stick or a computer and get the data off there. And the next slide shows just like course up a little bit bigger. The other thing that would be interesting is that we have the power regulation is currently a couple linear regulators for 5 and 3.3 volts, which are less efficient. And that's just this is also for our first development version of it. And then in parallel, we're developing a nonlinear power regulator that's not shown here. And if that is done in time for the final PCB, that will be integrated. Otherwise, we fall back to linear regulator. I think even with 2 batteries, we should have enough power. Just because especially moving the bigger feed to the Nosecone, it's not consuming power. The linear actuator for payload will be a very small amount of power. It's only firing for like a second. And yeah, so other than that, there's not the main work of this is the STM32 network, and we do have a prototype board from a class that used a similar STM32 that I was working on. So most of the schematics, that's what has been tested to a certain degree, and a couple of the sensors I've also accounted for to treat them. Next slide. So some of the main sort of failure modes been that I was thinking of are the batteries running out and we're just not recording data, or not having enough storage to record data, or failing to detect launch, which payload needs for calculating when we fire the linear actuator. So for the battery, we've done some preliminary power calculations, the preliminary results show around like 40 hours, just considering the power drain of a couple of the main power consumers, just doing a simple like, power requirement and that kind of thing. And the idea for testing it is to run the whole system for 24 hours, and it should still be powered at the end of 24 hours. That way we know that runs a calculation using all the power consumers. And then for data recording failure, the idea is just start a system, see if it records data, and be able to actually offload that data, read it, decode it, and know what it says. And then additionally, with running for 24 hours, we can also monitor that it can record data for that entire 24 hours and not overflow the storage. There have been also some preliminary calculations on just expected data rate from sensors and format we're using. And for launch detection, last year there was some work with the payload to develop some method of detecting launch using acceleration, because we don't get any signals from any of the igniters or anything like that from Canada. We don't have any signals going to the rocket. So the idea, which will be talked about later in the software side, is to use like acceleration, and it also pressure to detect elevation change. And the methodology for testing is to set those thresholds a bit lower and test in something like a car, where it accelerates for a certain amount of time, and we can see if the system is able to detect launch reliably. Yeah, and then the outcome is always to detect that sustained launch, as well as I just thought about this now. Forgot about the main slide, but
we should also test that just carrying it around does not set off detection. And just like general transportation to and from the launch pad kind of conditions. Don't just disable the whole payload before we even launch. So the general timeline is we had a bit of schematic review yesterday. The schematics were in there, and then there are a few changes we wanted to make, and looking for we'll probably be reviewing the PCB in avionics meetings probably after rain break, because there's only left our meetings on Friday. And then probably ordering PCB like 1st of March, and then looking to assemble and test in March. And there's an FDR currently scheduled for March 23rd, which is a bit tight for like assembling and testing and all that stuff. If it's arriving 2 weeks after we order it, I think we're hoping to have that sort of more worked out by the time we get there. I think that's next slide. That's it. Any questions? Yeah.
How are we going to activate the flight computer?
Yeah, so going back to the first slide, there's gonna be 2 screw switches. Yes, the current plan is to kind of shown in the pad where there's like 2 screw switches, there'll be holes in the rocket. And then like from there we like similar to last year. Yeah.
How will you be sure that the flight computer is active when you leave it on the pad? What do you have any visual indicators for that?
Not currently. Which is a good point. Yes.
Will it be transmitting when it's on?
Yes, it will be transmitting. So if we're getting data, obviously it's, but yes, I know like we don't want to rely on only that because it could be on and not transmitting.
What's the purpose of having the 2 cameras? I think thinking about it now, rather than like evening it out, I feel like the less radial hold we have of that size, the better. I don't know what the thought is around like, is it better to have 2 on either side, to have it be equal forces, or is it better to have just 1 on one side to reduce forces?
I think we have more concerns on delamination because it comes in that broader videos the time with you.
Could we like remove one of the cameras and reduce this to 2 batteries? Because I think currently the CAD is 4 and then move those over. And like I don't know exactly what I think the batteries are heavier than the cameras, but like you could move it proportionally. I don't know exactly how it affects things yet.
I still love to see you guys just, use a spy camera or move the cameras in parallel.
Yeah, well last year we didn't fly cameras. But the footage from Xenia 1 was nice to have.
Okay, have a successful flight.
Do you want a space launch type of thing where you take cool video of the rocket destroying itself? Or do you want no video of the rocket flying?
Yeah, no video for promotion.
No question there. Where, so the hole for the camera, which we're talking about, like it's definitely the largest hole we have to put a fuselage. Where is it relative to that bending moment and force diagram of fuselage?
Above.
So not in an area of height.
No.
Okay.
If you the highest bending moment is like on the lower fuselage, and then you have the coupler, and then you have
Okay, great. That's a good point. Is this hole, as it stands currently, is going through both the. So there's the coupled section that's in the lower fuselage and the coupled section that's in the upper fuselage. This goes through the coupler in the upper fuselage.
And then the antenna sits on top of that outside in the fiberglass section.
Yeah, the antenna's above in the fiberglass section, but this would go through the carbon fiber coupler and the fiberglass upper fuselage.
Just based on this design, all the antenna is like an inch above the camera.
Yeah, the antenna's going to move way up. This is not up to date.
Yeah, so that's the other thing is recently this decision to make within above or moving it away from some elements that may interfere with it, with metal and stuff, it will be moved above.
I'm also just wondering, because you mentioned testing it, for 24 hours, you think it'll be located with 2 batteries. Is that a plan to test the full transmitting capability of, and then the, deployment mechanisms after 24 hours, or is it just to see if it is still transmitting after 24 hours?
I would say probably, yeah, so the whole system plugged in and it should fire like or it has to trigger the linear actuator for like a second, like once during flight. So the goal would be to mimic flight as close as possible, so to have yes the transmitter on, but then to fire the linear actuator like once, and then keep it going for 24 hours.
I was just wondering, because couldn't be waiting on the pad for 24 hours until launch, or what's the time period for that?
It will be like maximum 6 to 8 hours. It will not be a whole day.
Okay.
Yeah, so
okay, yeah, that makes sense.
yeah, the general time in the past we've only spec'd for 6 hours, just because that's what we're expecting from as an absolute maximum from putting it on the pad, turning it on to landing. The extra 18 hours just to ensure that we recover it. In most cases, in the last 2 years, we've recovered it within a couple hours. So it's okay.
Recovery would be like the biggest one, because some teams actually spend up to like 2 days.
Okay, yeah.
Yeah, and another reason for cutting off at 24 hours is, well, for just like ease of like voting, but also the idea that if it's measuring the temperature for an entire 24-hour period and we haven't recovered it, there might be other issues, but also that I'm assuming that temperature can kind of be like roughly extrapolated for future days. Like if it's not even close to what our limits are, like once it's fixed, like the limit is like quite a bit higher, I think. Like it would have to be like baking directly in the sun, and if it's not for the first day, then it's probably not.
You might have also mentioned this you might be mentioning this later, but you mentioned sensor and data here. Are you collecting and transmitting positional data as part of this, or?
So for this system, we're not. For the simplicity of just developing a system. So the idea is we have the I think the next section is actually the telemetry section.
Okay,
yeah, but in general, we have 2 systems, and once caught, it transmits the things we required for competition to launch. It just like GPS.
Okay.
And then this one is for custom data, like status of the rocket kind of thing, almost like a proof of concept. Like if it doesn't work, we're like it's not going to be the end of the flight kind of thing. Okay.
What was Launch Canada's requirement for the overlap for the coupler?
1 cal. 1 cal in each direction.
Yeah. Okay, and how many holes would this put in that coupler? Total, including the mounting holes?
Including the mounting holes, 10.
Does Launch Canada have any restrictions on what that coupler can have in it?
Yeah, in terms of MOLA, I don't think officially they do, but also they inspect the rocket beforehand, and if they're just think it's gonna happen, they can just like not that's why that one did. So
I think most of the rules in general are like if you can like justify it like explicitly, they're okay with it. I don't know how much justification is given.
Is there any way if you wanted to put those cameras a little higher up above the coupler and use some sort of clear epoxy windshield for the cameras?
Marvin, is that possible? Sorry, using a clear epoxy windshield.
Can you
As a
embed
window
that
in
in
the
the
fiberglass?
somewhere?
I have no idea.
We
We'd have to figure that out. I mean, we could machine the profile so that it can sit up against it from the inside. Like take some kind of acrylic,
and machine it to have like almost like a round curve, like a lens with a flat backing that can go up against the inside.
They won't allow acrylic. They don't like acrylic, anything near structural.
Plexiglass. Okay, well, yeah, something like that, and we'd have to just etch it or something to make it clear and
Also,
see
would
through,
it
and it might
count
give
as
us
structural
crazy-
if we're just gonna like,
It's
it's
just
either
way
in
more
there or
than
not?
structural.
We
Like
can-
it, like, it's
We'll
like.
have to look into it, but it would be quite a feat for machining.
I think the camera hose actually above the coupler.
It's above the coupler.
It's above the coupling edge. So, the way it is with the drilling hose and tubes, not into the coupler.
I also kind of like the idea of making it one camera, because that also makes it, if we have the strain gauges, if those go through, then we have like a wire, we have space in the middle, we can just run a wire out of the bottom.
I don't know the rationale behind working with GoPros. Can we just select a different camera with a smaller lens? Because that would at least somewhat alleviate much of the, or many of the structural issues.
Yeah, it's just easier to work with GoPros and get them. And like we don't
consider the body of the rocket at all.
Yeah, the aerostructure's not my problem. So yeah, no, like we have looked in some other action cams, and they're just like, they end up being harder to work with or lower quality and brown, like the same size kind of thing. And,
I mean, I don't know if it's just anything, but Xenia 1 cameras I think work very well.
yeah, and that was with the Raspberry Pi.
Drone FPV cameras.
Those are even more annoying. Yeah, because like just because they're like a little bit less like self-contained, and like working with them, and we already are like have too much to do. So it's more of like we don't have time to spec like custom cameras and that kind of thing. Like the Raspberry Pi camera, technically doable. Chris is shaking his head no. It's technically doable. But it is a little bit slower. And then the nice thing about the GoPros, we just slide them with power, and we can press the button, and they just cycle.
Are there any other, this is more question for the structure piece, but are there any other holes radially symmetric with the camera holes? Because I know for Xenia 1, the camera had like I think real set screw holes that were like kind of in line with it, and that when Xenia 1 crashed, like it cracked there and it like went through all those holes.
I didn't think so.
No, right now, as you can see, it's just the camera.
Okay.
And it's, well, we have one on each side, right? It's symmetric, but that's the only thing.
There's something to note, they weren't set screw holes, they were the pressure equalization holes, so we also remember where those are.
Yeah, I don't know if the pressure equalization. Yeah, also you can figure out. More questions about like the electrical side? I think I can't remember next one is this one shoot or the structures of the anyway, fair.
Asking a bunch of questions and gas.
Yeah.
You were talking about the linear power regulator versus your, I'm guessing going for a switch mode, is that what you mean by non-linear?
Yes.
Okay, and that's just to be more efficient with the battery?
Yeah, it was just being more efficient, just because I mean some things like 5 volts and 3.3 volts, and then I know like inside the SDM it regulates down to 1.8 for some things as well.
What percentage were you looking at? What did you say?
I did some preliminary calculations on like last year, and a rough estimate was like 55% of power is being burned off basically through linear regulation. That was also because a lot of the power was coming from like two LiPo batteries at like anywhere from 8.2 to like 6.4 kind of thing, being regulated down to 3.3 volts to go to our like
bigger V transmitter, which was also connected to this. And so like you're regulating down from like 7 volts down to 3 and burning it off essentially. Yeah. So that was generally the thought behind that. And yeah, so it's not like critical if it gets on there. We're using 18650 batteries, which also are pretty dense, and we're not using a ton of power for most of the things on them. Any other questions?
Alrighty, so, I'm Charlie, and I will be presenting the telemetry aspect of the rocket flight. It's as mentioned before, this system is split into two, with the, COTS competition requirement, system, and also our custom data SRAM system. I'll be going over each of them in sequence. So starting up, we have the COTS transmitter. It's relatively simple. It's just, we've got the big red V right there, and it'll have the antenna mounted right on top of it, directly to the SMA connector, pointing right up. Powered by a single 18650 battery. It's simple. It's been done multiple times before. It's been done in the Hayek 1 and 2. It's very standard. Almost every single team uses this. It should be completely fine. We'll obviously test it, but it's a proven design. Next slide. Now we have the receivers. It's the same system for the SRAD and the COTS. They're using the egg beater antennas. Same deal as before. They have relatively low gain. However, they're omnidirectional, completely hands-free operation. You can just put them down, as you can see right there in the back. That's actually the 915 right there. It's just standing on its own. And yeah, we will have one for the 915 and one for the 434 megahertz bands. We'll also have Yagis as backups in case something goes wrong, because since they have an incredibly high gain, if we can't receive it with the egg beaters, it is very likely we'll be able to receive it with the Yagis. And thanks to PDR, we've actually built it, and the FWR readings are actually quite promising. 1.3 you want 1.5 and below, so it's looking pretty good. Next slide. All right, now for the fun part. The SRAD transmitter. This is a modification of the antennas that we have done on Xenia 1 and Xenia 2 in the past, except for two primary differences. First off, it is going to be shortened to match the 9 to 15 megahertz band instead of 434 megahertz band, because that's what this little guy here is for. We're still working on simulating, so final dimensions are not done yet. And it won't be on the outside, so it doesn't get torn apart by supersonic flights. So it'll be mounted on this little mount right here that is mounted on the inside of the rockets. If you go to the next slide real quick. This is preliminary, very preliminary simulations for that antenna. This is what the current gain plot is. The redder it is, the more gain it has. So it has this rather weird shape that Isla and I are still not sure why exactly it's happening. We're working on it. These match like 1-to-1 of what's like this propagation pattern for the antenna in this position. So these correspond to these points here. And hopefully we will have that done soon, and we'll have a better propagation pattern to show. Next slide. All right. Can you by any chance reload the slides? I had to add something last minute. I'm so sorry. All right. Now, for the assembly, as mentioned previously, it will be attached to the flight computer. It will actually be moved above all PCBs. This current CAD does not reflect this. The main reason for that is we need to keep both the toggle link right here and the carbon fiber coupler out of the near field of this antenna. Otherwise, it will cause interference and it will become a trash antenna. And we don't want that. So, specifically, we want it out of this red circle here and as far out of this green circle as we can as well, because it gets a bit funky in here, but it's not game breaking. We do that. It will be attached using posts on that same mount before, and it will be attached to this board here using an RT316 cable with a length of quarter wavelength. All right. As for testing, we have an extensive list of failure modes of one item, that being loss of signal. There's really nothing else that can go wrong. The problem is it can go wrong in, well, a lot of ways. So the three main ones that we're going to need to account for is non-line of sight due to trees, which anyone who's at Xenia 1's competition will remember what a problem that is. Excessive path loss is actually one of the primary concerns at the moment, because this antenna typically is rated to 4 kilometers. We need to extend it up to around about 10 just to be safe. And alignment loss, since this antenna is shorter, Isla and I are not completely confident on if it'll have strange blind spots. We have backup plans in case it will have a weird blind spot to account for that. But basically, to account for all this, we're going to transmit just through trees. Probably, I mean, we could probably just use some of the trees there. Transmit over a 10-kilometer line of sight and just spin it while we're testing. It's relatively simple for something so complicated. And next slide. As for our timeline, we want to get the final dimensions done by February 13th, which will hopefully give us the tolerances for distance from carbon fiber to copper and taco links, so that MacLeod doesn't continue to go insane. Also, hopefully we will verify using the anechoic chamber that is somewhere over there. If we have time, we'll run another 4-kilometer mid-range test February 15th. And over reading break, I'll be trying to find a 10-kilometer line of sight. I'll probably be reaching out to the Dominion Astrophysical Observatory, because from Bob Wright right there, all the way to the Plaskett Telescope is about 10.5 kilometers if memory serves. As proposed reading break, basically just run a long-range test. Gets the receiving board designed by the end of February. Crap, I forgot to mention that. And have to mention training the antenna by the end of March. Can we go back a few slides? Actually, that was good. Actually, no, 2 more, 3 more. There we go. So there is actually difference for the receiving antennas this year. There is going to be a specific receiving PCP. This will both incorporate a low noise amplifier and filters, because last year, especially Chris, will remember the fact that the egg beaters did not get the best signal because, once again, they don't have great gain. So we need to incorporate a low noise amplifier. But anyone who's at Xenia 1 will remember that the low noise amplifiers will explode our RTL SDRs if we're not careful. So what we're going to do is we're going to include a low noise amplifier and limiters and low band pass filters, something pass filters, I forget which one, in the circuits, in order to make sure that we don't destroy anything, but we actually get our packets. It'll also be significantly cheaper to make a board individually, because if we were to buy each of the parts individually, it would be like $50 a piece. So we want to avoid that. And that is all I have to present. Are there any questions? I believe Gordon was first.
I know you guys tried to test antenna. Can you just give me context, like what happened in that test?
Okay, so in that test, basically we borrowed the antenna analyzer from the propagation lab, brought it down to the room, and we tested the SWR, which is kind of like, it's kind of a ballpark. It gives you the basic estimates of how efficient the antenna is, kind of, sort of. It's weird.
It's the energy reflection coming off of the antenna of your signal, so it's a ratio that helps determine the power transfer to the antenna. Yeah. So really, yeah, in a sense, it's how efficient it is, but it's not quite the best way of putting it.
Basically, anything that is said about the properties of antennas will be it's this, but not quite. Just everything with a bit of grain of salt. So we tested that of all the antennas. We actually found that the egg beater is not the egg beater. The Yagi is not great and needs some repairs. It's just been brute forcing through all of its losses. It's 3. We've been using it for a long time. Yeah. It's not that bad, but keep in mind that one over there is 1.3.
Again, we had this conversation. SWR more than a grain of salt, like. It tells you how much power is going somewhere, it doesn't tell you where it's going at all.
True. But other than that, we also did test like the rough estimation for the lengths of the transmitting antenna. It unfortunately doesn't tell us much, but it did tell us that the closer we got to carbon fiber, the higher the spike in its SWR was. It was, and unfortunately though, we need more tools and more data in order to actually figure out what the distances can yield. It was more of a curiosity and testing our test apparatus, which despite looking like garbage, it actually worked very well. All right, Matthew, I believe your hand was next.
Yeah, so I've got two quick ones. Is I think it might be worth testing to more than 10K because of the fact we're flying to 9.5K. It's going to move probably about a K horizontally, and we are not going to be sat at the launch site.
Right.
So it's going to be probably, I'd estimate, like mental math closer to 12K.
Oh boy, I don't know.
The thing about this, and like the other thing is like this is the secondary system.
Yeah.
So like,
We'll still need to test the cost system in this way too. So we
yeah,
will
yeah. Okay,
follow
so it's a good
along.
point for the testing the cost one actually, but even the cost one, if we lose it for like a bit at apogee,
yeah,
it's not the end of the world because the most critical points are when we're launching because we can't launch with it unless we receive signal, and when it's coming down.
Yeah,
and we want to recover it. We need to know where it is.
If the wind is bad, assuming the lane doesn't tangle this time, it might just start drifting away from us.
Yeah, do we have an
So,
estimate of
yeah,
how bad that drift can be?
I can get you some numbers, I don't know anything, but like, the bigger the range, the better, it's not like.
Oh, yeah, yeah.
Because like, I mean, if we're considering worst case here, let's say there are terrible winds up there, and we have like a failure to deploy, and like the main deploys at apogee, it's gonna land in a different fucking time zone.
Either
So
way.
it's not.
We'll just pick it up in Victoria.
Yeah.
Either way, I'll also start searching for lines of sight that are 12 kilometers. I'll still reach out to the DIO though, because that is still a very convenient line of sight.
Yeah.
VR.
So I had a couple questions about the actual antenna. Specifically, you have a mounting, can you go to the slide with the antenna? Yeah, it is that one, the actual ring antenna. Yeah, you got this fixture for holding the end, like the copper strip. What is that? What are you planning on building that out of, and what sort of parasitic are you expecting in the region around it?
It's 3D printed, and parasitic would be a question for Isla. Unfortunately.
Okay. Also, could we go to the one with where you've got the this one, just looking at the game plot, it looks like you've got a null coming around the section where you've got the break in the antenna.
Wait, as in there?
No, that's the P point.
Okay. So, oh wait, you mean the end?
Yeah.
Okay.
So that might cause issues. You might want to look into a way of making this antenna a bit more game.
That's what we're hoping to do, and that's why the simulation isn't quite done yet.
The easiest way to do that would be to shrink it so you lose that break in the loop.
Like you mean make it into an actual loop antenna? Because
Yeah.
this is the dipole antenna.
Yeah. Yes, bent dipole antenna. Which is why you have the nulls. I was in the weird little thing.
But a loop antenna, you still get nulls that
But-
just point in different directions.
Yes, no, but you can't ever get rid of the nulls. This one has this has that really nice gain in the downward direction, which is good. And the nice thing about the egg beaters is because they have their max at around 60 degrees.
Actually, not these ones. These are the Egg Beater 2s. Egg Beater 2s have their max pretty much almost at 0.
Oh,
Wait, hold on. 90.
Senate.
Yeah, no, direct the horizon.
Oh, okay.
Yeah, it's Egg Beater 1 varieties that are just the circles. Those have their maximum at the top. I think we kind of want to go, we're still debating whether or not we should go for the circles or for the squares, but currently, since the squares have the biggest gain on the horizon and the most critical bit of tracking is right when it's about to land, figured that would be a good option. Still in discussion though.
Any other, Matthew?
So for the SR antenna, that is purely like we're expecting that to read from the egg beater because tracking it's going to be difficult when it's like higher than Everest.
I'm not sure what you're asking.
Like in terms of like, I'm hoping it's reliant purely on the egg beater, which you're not hoping to track it with like the Yagi, right?
We're gonna do both.
We can
Do both, but I presume the Yagi isn't going to work because you'll lose line of sight.
Yeah.
True. But you can also kind of just get, it's so long as you have a lock, you can kind of still carry it up. Like I could not see Xenia 2 while I was tracking, it was still able to hold the lock. Somehow.
Yeah, for Xenia 2, I lost like all the packets at the top. Like I had nothing at Apogee.
Yeah.
That once again, that was without the low noise amplifier, so that was the main.
But as you say, we're going to get the important packets close to ground level.
Yeah, it got much more when it got closer.
Okay. Okay, that's good. That's good. And then the last one that I had is if you go to the slide where it showed the full assembly within the rocket.
Can you forward one slide?
Yeah, so like I'll just start to point out. It'll take too long to describe. Is essentially so basically this is going to go right in the middle of, so the carbon fiber ends here, obviously Taco links up there, which means this is moving up a bit to roughly where the screw switches are right now. So those are just going to have to get relocated a little bit.
Yeah, we might like, wait, is there space to move like the bottom of this beat down slightly, or is it right on top of the battery?
I don't know.
But it looks at it, doesn't look like the lowest PCB is only there because it can't go, it's not able to phase through the antenna. So I would assume.
We'll have to check that out after.
We'll have to look at that. Brandon.
Showing the three-dimensional polar plot there of your antenna game. What's wrong with that exactly? Like that's exactly what this antenna was designed to do.
Yeah. Well, it's not what we were hoping for. What were you exactly? A little bit better.
Which way do you want?
Like in what way?
Yeah. What does that mean?
That's an Isla question, unfortunately.
Okay.
Yeah.
Because that's got decent gain.
Yeah, no, the gain is good. I think it was the blind spots are a bit awkward. That's all. But we're not gonna be able to fully escape blind spots.
Yeah, but I mean, like most of the time, like we're not gonna ever be looking at those blind spots.
Sure.
If you really wanted to get rid of those blind spots, you'd have to have two separate antennas out of phase and then transmit back and forth between the two of them.
So like that.
That's still one antenna. What I mean is two physical, like that one's, there's one antenna feed coming out of that, is there not?
True. Yeah. Oh, you mean like an actual array with two powered elements?
I mean, an actual array with two powered
That
elements.
is one of the solutions we are debating, but we're not sure if we're gonna be able to make it work.
I don't think we could do it in the time.
No.
Just because like, yeah, like our everything else is designed for just like one transmitter, one line.
Yeah. But yeah, the question is that you have to answer for yourself on this is where do you want your nulls? Because if you really care about those side nulls, then you're gonna have to change your antenna design. But if you're okay with having your nulls say at your zenith and your at the very bottom of it, then you want more of it. You want to turn it into more of a ring antenna, or which would basically be a loop antenna that acts almost like a dipole.
A large loop or a small loop?
You could, well, with this size, you could do it pretty much with a large loop, with the like within the structure. Either way would work, but because either way you end up with your you end up with your with the orientation of this antenna. If it were in such a like case, you would have your nulls directly pointing upwards and directly pointing towards the engine, versus what you would be the side nulls you have right now. So the antenna design really depends on where you are okay with having your nulls, and what you're expecting your flight pattern to be, so that you can gain maximal contact with the rocket at all times.
I'm all about like that.
So combining your flight profile with what your propagation pattern is going to be will really tell you a lot about that.
that in mind, yeah, this might actually be our best bet because Mel's up and down, considering the rocket is usually pointing right up. That might be our best bet actually. The only time it might get a bit weird is when it flips sideways and it still has some good point, and it's not like the entirety of radial is dead.
Most of the time, we're looking at it like from like the bottom.
But that's more from the side there. Not like, it would probably be from, something like that probably.
When it's high up, like it'll be the bottom. Yeah.
On that plot there, what is the point, like, what is the angle of 3 dB loss of your null? Like, the opposite of being. So,
Can you
your null.
rephrase that somehow?
So, at some point in there, in that yellow section.
Yes.
You're getting 3 dB less than isotropic radiation, correct?
Yes.
Okay, what's the angle of that?
I don't know. I don't have the simulation files running on Alice's computer.
Okay.
You have the forward plots.
Secondly, then, I guess the question would be,
Simulation
is,
breaking a little bit.
do you ever expect the rocket not to be spinning?
No.
So then it'll be.
Yeah, that's another point of why.
It's nice having them horizontal because you don't care about losing packets, you care about losing all packets.
Sure, yes.
Yeah.
You're right, yeah. All right. Are there any other questions?
Just make sure your transmission period is greater than your rocket rotation period. Or
Look at that.
vice versa.
All righty. Thanks, Charlie.
Yeah, like sleepy.
Like laser now, it's Chris.
Okay.
Cool. Hello, people, mainly mechanical people. I'm Chris. I'm talking about software today, so hopefully your eyes don't completely glare over. Yeah, so just quick terminology on a couple of things. We're using free art classes here. So that means there's a couple of words I'm going to be talking about. We have a task, which is just a single process, and then we have a job, which is a collection of tasks to complete one goal. So those will all happen at once. Okay, we can move on here. So this year we're using free RTOS, which is a real-time operating system. So there's like a layer kind of below or around the hardware layer that just kind of runs the scheduler and runs everything. So when tasks actually happen. The reason we're doing this is because of payload. Payload needs really firm deadlines, and RTOS is 4 firm deadlines and for very hard deadlines. So instead of doing a super loop, which you normally do in an embedded system, so I'll just have like task after task after task, and sometimes interrupts pulling tasks. We'll have a scheduler telling us when tasks are happening. For the system requirements, we're just using this chip. It's above all the requirements that you need. So hopefully we won't have any memory leaks. Yeah, we can move on to the next slide. So for the scheduling stream, we're using priority-based scheduling. So some tasks will have higher priorities, so they'll be having probably more time in the scheduling. Other tasks will have lower priorities. Some tasks will be periodic, so that means they'll happen every period. So you'll see like, this is just an example. So this is not actually ours, but you'll see there's an A here and then A will show up again, and then it'll show up again. So that'll happen for like things like sensors, and then aperiodic tasks like when we're detecting apogee. That'll happen at later times. Okay, go on to the next slide. All right, so here's a breakdown of all of our jobs and tasks. You see from this column, these are our jobs, and then these are the tasks associated with them. So for reading, these are going to be periodic. We have our sensor unit, sensor suite here. We have the AJAX, so this is acceleration, IMU. I think only gyroscope now. We've changed this since last year. The BMP, which is pressure, and what else is it? I don't exactly remember, but and then we have strain gauges. So this is not with I2C. This is our own fun connector, which we're not talking about today, but
And then we have the temperature array and payload, so all those will be read. We have a high priority on the 80X, thank you. Because that is being used for launch detection, so it would be better to get these packets all the time rather than the other packets. And then for writing flash and transmitter, those will be happening periodically right after the reading happens. So we'll go reading to writing, and then these will happen periodic. So we'll have the first one, which is launch detection, and then we have a timer for apogee, and then we have activating a linear actuator for the payload. Okay, so we can move on. Okay. Wait, back one. Okay, here's how our research is going to work. So we have queues for each sensor. So basically, when we sample the sensors, they'll be sent to individual queues. So each sensor will have its own queue, and then the transmitter and the flash will read from these queues when we are writing to them. So this way, we don't have to deal with any deadlocks and mallocs when one resource is trying to be accessed by a bunch of things a bunch of processes at once. So that's the reason for this configuration here. And the task queue is basically just when tasks happen, when they're happening periodically, they'll be in the task queue. And this is just done by the OS scheduler. And then all the tasks kind of read through this and they happen. Yeah. Okay, so just brief overview of all our reading. At the top here, we have all our I2C sensors. So these will be daisy chained off of each other. So we're just using one I2C input. So that means we'll have all the same data rate, all targeting 80 Hertz. And then the ADX is the one with a higher priority, which I'll get into later. And then for the strain gauges, it's just also 80 Hertz. The reason we're choosing 80 Hertz for everything is because the strain gauges is capped at that. These ones can go faster, but we're sticking with 80 Hertz. And then the temperature is, we can chain 4 sensors off of one, so we can read all the 4 sensors off of one line. So that's going to be happening there. Yeah. And then writing, we're just going to be writing directly to the flash memory, and then telemetry will be writing over UART to the lower dev board and then sending it off right away. So that's that task. Okay, here's the fun stuff. So stuff before this was just kind of data logging. This is where actual computation happens. For launch detection, we're gonna have 2 algorithms that we're gonna use. We're gonna use a hot sustained IG. Let's hit this one here, and then we have just basically a change in altitude, which is this one over here. So for the sustained ID, we'll basically be sampling a bunch of the acceleration values and checking it against thresholds. And we'll be checking those happen after, I would say I think Grayson said it was 50 milliseconds was what he tested before with current use, but we're also going to test and figure out how long it'll be at the sustained G for, so we can actually, so we don't want to misfire and not have the actual launch detection. And then the other one to check it is actual change in altitude, and that's done through pressure. So we're doing some calculations. And then we're starting a hardware timer after we actually detect launch. The reason we chose this is because the equations for detecting or predicting your launch apogee while you're going is very complicated. We didn't want to do that, so we're going to go based off of the simulation timers because we need it to happen right before we hit apogee for the payload experiment. So once that happens, it'll do the linear actuator once the hardware timer ends. It'll do the linear actuator, and that's pretty much it for the payload stuff. And it'll continue reading all the sensors throughout all of this process. Yeah, so that's kind of what this flow diagram shows here. First, we detect launch, run the 2 ones. If one triggers it, we'll start the hardware timer. Hardware timer goes in the background. While this is happening, all the sensors are still reading and sending data to the flash and to the transmitter. And then once it happens, once it comes back, once the hardware timer is done, it'll activate the LNA and it'll kill the task. And then that's it for payload. All right, so just a quick aside. For this year, we're doing automated software testing, and this is just kind of set up for this. Yeah, it's not too important, but I just wanted to mention that.
Okay, so for testing, we are gonna have unit testing for the payload algorithms. So with the test bench that I showed briefly before, these will run every time we have a pull request, or well, we could also automate it so it happens every day at a certain time. So they'll just test the same unit test based on whenever we change the code, and they'll see it'll run on the actual system and see if it works or if it doesn't work, and it'll give you a report of how your tests go. And then we're also going to be doing like a sensor reading, so we're going to check if sensors being read to the correct places and if they're being read to the queues correctly, because we don't want things to mess up with memory errors or anything like that. And then for full system testing, we're going to use old flight data from Xenia 2. We're going to pipe into the system and see how it reacts. Yeah, and then for integration testing, we're testing between writing and reading files. We have a bunch. There's going to be a bunch more tests written as we go, but this is the general one so far. Okay, on to the next stop. And then for the timeline, as you can see, the strain gauge driver was done like last year, so that was done. And these are the drivers for the EMP and IMU, so those are already done. And we have a prototype board that works for that, as Mateo said before. So we can test basically most of the system already. And then once we actually get the new dev board that we're designing right now, we'll set up to the test bench, and then we can start testing all of our things here. But everything kind of goes on a linear progression here. Yeah, so that's all. I think that's all for me. Okay, questions? Yes.
All right. All right, let's start with the reason for this whole computer. Essentially, the most important reason is for payload.
Yeah.
Correct?
Yeah.
So why does the syringe, and it's nice that we have all the payload people here today.
Yeah.
Why does the syringe need to be activated before apogee, and how much before apogee?
So we want there's more information on this on the actual public slides, but what we want to study is the effects of flight leading up to apogee, but not after apogee. So we want to have the high G conditions of launch and then flight, and then microgravity effectively at the top. We want to be able to study that, but we don't want anything past that, because it sounds like they're studying.
You don't want the shock loading of the drogue chute. It's
Yep.
one of the big hard ones. So
Yeah.
it's kind of what I was going for on that question.
We don't want solid none of that. So the actuation of the fixed agent has to start after the microgravity period starts. It's not like there's no exact point where that happens, but
yeah,
roughly in that area, and it has to finish before apogee.
Yeah, you're gonna have high G's, high positive G's, then relatively high negative G's for a short period. Then you're gonna have a very short window of microgravity, if you will.
Yeah, there's about 9 or 10 seconds of that, like
Yeah,
less
that's
than 1
pretty
G.
And is that where the fixing agent has to take
Yes.
place?
Yeah. So I can't remember the exact numbers based on how much power we we're giving the linear actuator and we were using, but I know for sure our actuation time was well within the numbers.
So the reason I'm asking all this right now and not as part of payload.
Yeah.
Is because you're choosing to use a hardware timer based on predicted flight.
Yeah.
Rather than using what I think would be a relatively clear indicator of that near zero G period. It'll be before apogee.
So we could add another algorithm to test that.
Well,
I thought that was the plan.
yeah, the reason for not using acceleration is that, like, yeah, you can know that you're like getting lower, but it's hard to know how close you are.
I mean, the question is, do you need to?
Well, yeah, because there's a certain amount of like that activation time to like for a second or something to activate the linear actuator.
Yeah.
So you need to know that you're more than 1 second away from that like apogee event, whatever. But like knowing how close you are.
Which do you think would be a better prediction? Predicting from the moment of launch, or predicting from the moment of reaching less than, 0.1 negative G's?
Yeah, I mean the logic behind going with the timer is based on the simulation we do on the ground is a lot more powerful than anything we do in the sky. I guess we could
use that to know like what acceleration we're expecting to be that's well within, like well far enough away, and then vary based on that.
Yeah.
So that could also work, and that's probably more reliable, I'd say.
That's where I'm going with
Yeah.
it. It's like changes in pressure, density, humidity, all that stuff will change your time slightly.
Yeah, yeah.
Especially from launch, but once you get to that like negative 0.1 G's, you know, you're probably still going 100 and something kilometers an hour upwards, probably even more than that. I think that point in time will be a lot more predictable. So if you can find that using your accelerometers, you can then use a hardware timer from there.
Yeah.
So you're saying change where we start the hardware time?
Yes.
Okay.
So use your.
So we have a launch event and then we have the other event at like the 0 G's. That's what you're saying. Okay. I mean, I don't know how we would test that to make sure that that would
I think
happen,
it's actually easier to test than like, or I think it's more reliable because then we don't even have to check.
Yeah.
We don't even have to know at launch.
It'd be a good idea to know at launch, just to be like don't look for this level of G-force before you get there, because you know, God forbid somebody mounts the rocket.
But it might be like look for that like low G for like 5 seconds.
Yeah.
Yeah. And then like if you can chuck it high enough to it's in like thermal gravity for 5 seconds.
Yeah.
Hopefully we're not doing that. I mean that then the like accuracy of the sensor comes into play, and we haven't been considering that up. Like how accurate, like or like if it's accurate enough for what we would need.
Right. Okay. That's a good point though.
I just wanted to clarify what my understanding of our discussion of the algorithm was that we would have several fail-safes. We have a couple different ways to detect actuation time. We were going to use altitude. We were going to use like experiencing less G's. I don't know if we can actually.
You mean for detecting apogee?
For effectively, yes, but what we really need to detect is when to start actuating, which is just before action. Yeah.
Yeah.
So if I remember correctly, we wanted to use time elevation, and possibly like forces experience. I couldn't remember if we not forces, sorry, but like the same sensors we're using to detect high G at launch theoretically would need. So you would like you have it. And also there's the oh shit of if we're going down, we have a problem, activate immediately and do damage control.
Sure. Yes.
Yeah. Oh, I thought from that conversation we got that it was using backups to detect launch.
Yeah. The timer is more of a backup than the real thing that we're trying to get.
What's your minimum amount of time in micrograph?
Minimum amount of time. What do you mean by like during the sim or how should we
Like-
don't have an official minimum. We want to max. We need to experience at least some amount. I'll let you know. No. Yeah, maximize it as much as we can, which I know is very much a science answer and not the engineering
We're
answer.
going over to the point of drone deployment is a big.
Yeah, absolutely.
So.
You better go early.
So it'd be nice to have all these numbers and know all these things, so we can figure this out.
I think.
Yeah.
I think we have them in documentation. I just don't know them all.
This is gonna trend with these reviews. It's
Yeah.
constraints on payload.
Yes.
Yeah, that's always what it is.
Best idea on timing, I think, like, just from the outside view.
Sorry.
From just like thinking about predicting apogee, I think our flight sims are really good.
Yeah.
And I think
See, that's
they'll be the
thought,
closest.
yeah.
I think they'll be the closest. So just like time after launch to actuate is gonna be your best bet. I think
Do you run the sim?
even if it's off by a second, it'll be closer
Exactly.
than anything else. we can do.
That's why we initially thought that would be fine, but we can have multiple ways of making this happen. Hopefully they don't counteract each other.
That's why you're the programmer, so
Yeah,
you can make sure not,
So we gotta
don't let
test
us
that.
program it.
I don't know if this is necessarily still an issue, but when I parsed through the Xenia 1 flight computer data for acceleration, the total magnitude of acceleration was 7 on the ground instead of 9. Or 9.8.
What do you mean?
Like,
Yeah,
like 7
That was in
7.5 meters per second squared.
That's in G's.
That's it. Okay, on resting on the ground.
No.
What?
Yeah.
Oh, so you're
No, no,
saying the
it-
the sensors were
The sensor was at least that's what I. Oh,
Yeah, no,
We're-
like,
we're talking
it
about
was a
some
meter
other
second, and
things.
it did go to 7. One of the axes, I think, was.
They just fluctuate a lot. They go like.
no, it was consistently at like 7.5, so just resting on the ground after touchdown. So
No,
I
it
don't know,
was-
I
it
don't know if that was an
was.
anomaly, but like I just looking at these. might
So the
not be
sensors
best way
are
to do it.
not great, is what you're saying.
We are using different, like,
Oh, fair enough.
we are buying chips for those sensors and putting them on the board, so they're gonna be like from the back.
Yeah,
As long as that's.
rather than a breakout board.
So next question is specific to your software process there.
Yeah.
Queues.
Are they hardware things that are separate from the main process, or they're just gonna be software?
So, yeah, those queues aren't really saving the processor any energy.
It's more of like having things in parallel.
Yeah, that's
Uh,
more
so
the
we-
reason for it.
So you can be doing things in one way and have like it's not the most efficient to say save it to the flash after like every single reading.
Okay.
So it's basically like, yeah, the flash might wait till there's like 100 values, then save to flash kind of thing. Like it can happen less frequently. So it's doing it all at once. And that might happen at different rates from sending it to like the telemetry system. And yeah.
So these queues are in the, just in the hardware registers. On the actual CPU.
Yeah, or memory, however the program decides to.
And that's only because it's faster than writing flash.
Faster than writing it in like all the time. Like, because it's kind of like.
When you open a file on flash, like.
Yeah,
Close out that sequence, it takes time.
Yeah, so like, yeah, you have like the processor, and then internally it has like the flash memory, and then externally it has the like external flash, and it's just like going to that internal memory is like super quick, but then walking all the way to like the flash, it has to make hardware calls to peripherals to all that.
Yeah, I thought the queues were trying to like prioritize processor time, but they're not, they're just trying to make.
It just is more mutex than deadlocks rather than. processor
Yeah,
time.
and then there's different, so like, and then payload has to, like the payload calculation stuff has to process that data, as well as sending flash.
Yes. Yes, Cam.
The payload question, but as regards to activation time, how long does the fixing agent take to fix the samples after being injected? In days. Cool.
Yes.
Going back to the simulation time and payload, how precise does payload need to be? Like, say your sim, it's, a little bit windier today. And so how precise do you have to be? Like, is it, if it's within 2 seconds, you're good. If it's within 15 seconds, you're good. If it's,
It's good to know what is our.
This is a better Gordon question, actually, because Gordon was saying, what was your maximum variance in your simulations based on the different conditions? And I don't know what your rocket motor power is, plus or minus, but.
I think a rocket motor would be very consistent because it's like it's manufactured commercially. So
I'm sure it has specs though, right?
yes, but the
Oh,
specs
everything
you
has
get
a tolerance.
from the prospect from the motor. So we need to have them that is consistent, but you're taking not to back any
Error value.
exactly. Yeah. So but condition wise, environmental, like of course will be the biggest because sims have their own assumptions and those assumptions cause errors. But under like different condition, I don't think it changed that much in terms of like timing.
So
wind speed would change. So
What if you change your coefficient of drag by 1%?
that's something that we don't know. That's something that we're waiting on.
I'm gonna guess that your coefficient of drag is not gonna be accurate.
No.
1%.
Yeah. So we're waiting on the accuracy.
And this is why I'd be worried at those, at Mach 2. Like, yes, your sim gives you a consistent answer based on consistent inputs, but if you change those inputs by a little bit, how much variance do you get?
Exactly.
And if that's 10 seconds, that could be worse than going with finding where you get, 0.1 G and.
Yeah. Like if you take, 100 different sims and average it out, like what is your average time? And what's your standard deviation versus your mean time? Because you could run into a problem, but if payload says, oh, you're good within 10 seconds, well, it's less of a problem. But if they need to be within half a second, it's gonna be a huge problem.
That's something that we need to do a sensitivity analysis on like certain values. So yes, it's a roadblock that we're kind of stuck on a CFD. But that's something that needs to be done for Halo. So
It'd be the big deliverable of this is find like work between the three groups of you, software. I don't know what you guys are calling, like that's the structures is handling aerodynamics as well.
more like
Analysis, so structures analysis and payload and all of you guys. That's the one like kind of gap I see right now. It's getting that.
So what is the timing of like that timing?
Sorry.
Like before.
So it has to happen before FG, if it happens after FG, that makes the analysis extraordinarily difficult. Yeah, it makes it impossible. If it happens after FG, there's versus.
How much earlier?
I would break this down. I would do this outside of the day. Break it down as a flight profile. So if it happens here, if it happens here, if it happens here, if it happens here, and figure out like how good or bad that is for their experiment. And then you do a risk analysis on those points and figure out which one you shoot for.
Give some context, like I don't have an exact number, it's based on several different things, but just getting an estimate from the linear actuator supplier on how it actually, I'm gonna give a really rough estimation that actually should probably ballpark 2 seconds, which means
That's slow, really?
like that is a maximum that I am expecting here.
Okay, I still know the last piece.
Yeah, I don't like that at all. Sorry. So given if we've got like a 9-10 second window, then we have fudge factor.
Right.
It's
Alright. Did we write all this down? Did we?
Does someone particular-
I mean, we recorded this all, so we can listen to it later, but it's good to know that you're here now.
Yeah.
Okay.
Any other questions for Yannis?
Yeah. Cool.
If you were starting on assembly, that's my reason why I would prefer against on putting it on the motor because it's very difficult to assemble. So the first we basically assemble everything you see here. Everything will be ideally pre-assembled. It will be pre-assembled at either like hotel, any like not on the launch site. So we have everything here pre-assembled. We get on our vehicles, we drive to the launch site, set up everything, and then we simply do the following process, which is, so we start integrating the motor, which we just slide from the bottom and attach with the boat tail. Next thing, you put the pre-assembled flight computer and payload into the lower fuselage. Yes, like this. AKA why we don't want to put it on the motor. Next thing, this assembly will be like attached in one single assembly that you can hug it like a baby, carry around, and then we put it in the upper fuselage, which there's radio screws here that we fix. Okay, so now we can put our upper fuselage and recovery assembly into our lower assembly. So now it's only left with the Nosecone. So the last step will actually be taking the links here, link it up to the eyeball, and then just attach our fuse. So this is like 5-step process, which is pretty simple. Unlike the whole design concept of this rocket is to make things modular enough that we can put it together easily, and we want to have modules that we can check on everything, follow our checklist, and then just put them together like this. So we do not spend 6 hours at the launch site trying to figure it out. If anyone watched the vlog yesterday, you will understand. Yes, thank you.
Just with the Nosecone, I think your plan was assembled before it's launched pad. We'll have to turn on the bigger V like just before we. So like, what is that like assembly?
So that's something that I think this assembly is missing is how do we turn it on like either with screws or like wireless, but.
Well, yeah, like I was thinking, like, cause in my head, I was, okay, we just turn it on and then we put it in the rocket.
Yep.
And then it's just on, like we don't need a physical way to access it. But is it even possible, like, I don't know how it gets into the nose cone, so I don't know what that process and how long that process, or if that's too complicated.
It will be on an assembly, so I will let you.
So I'm a big proponent of not like just turning it on and then putting it in.
Yeah.
Basically, you can just assemble the entire support structure for the big red beam and the bulkhead, and then just leave it as is. And at launch sites, after we're done assembling both the fuselages, you just turn on the big red beam, put the nose cone bulkhead into the nose cone, put the set screws in. Now it's on, and then you can assemble everything. The reason for this is I mean, this is not an analysis thing, but like I don't think we should be putting screw switch holes on the actual tapered profile of the nose cone. And if we do put screw switch holes on the flat part of the fuselage, that's going to compress the recovery bay. But we already compressed the recovery bay as much as we could, so that's just going to have to lengthen the rocket. So I think the best way to do it is just you turn it on before you put it in, and then the one life would last like what, 8 hours, 10 hours, something ridiculous.
Like 48 hours.
Yeah, like 48 hours. So it's fine.
Okay, go back one slide. On this bulkhead, on this side of it, we put a screw switch.
Yeah, and
We
then-
turn in the screw switch, we put it on, and it's good to go.
Yeah.
We can put a hole through the bulkhead.
That's what you just said.
Yeah.
Basically, we somehow
maybe not
have it so that we can access it through this bulkhead, whether it's a screw switch, whatever it is, but we have it something that's a switch here. We switch it on, we put it on, it's good to go.
If it's a 48-hour thing, why don't we just turn it on? We lose 2 hours out of 48 hours in this. So like the flight lasts what, like 10 minutes maybe?
No, you don't want to broadcast your radio like.
Oh, fair enough. Yeah, that's fair.
Like, it'd be really great to have the nose cone assembled with the thing inside before we leave the hotel, and then, yeah, you take it to the launch site, turn it on through the bulkhead, and just put it on.
Yeah.
I don't wanna be installing the bulkhead.
The only
on the
thing
nose
is,
cone.
it's also nice that like when you turn it off or on, like during the day, or like you wanna. Like that kind of thing, it is kind of nice that we can just like, without disassembling it, just turn it on, off and on. Cause otherwise we would have to like, you know, undo all the screws and stuff.
Yes, 6 screws, but yeah, okay, fair enough.
I think Ryan.
I was gonna say.
The only thing is, we have to consider the fact that that bulkhead acts as, like somewhere for the pressure to push out the nose cone. Obviously, it's a very small hole.
Yes,
But-
I think Tim mentioned like we don't really need that feature, like ceiling feature, yes.
Yes, we don't really need that. How does big red beam interact with very hot gas? As long as it's not gonna damage, because we can just adjust the black powder a little bit to fill up the extra volume, and the surface area of the relative surface area of the nose cone is the same on the vertical, on the axial direction. So that's fine for recovery. I just don't want to damage any electronics in there. But yeah, no.
I don't think there'll be enough.
Yeah,
For the
like-
gas to get in there anyway.
Yeah, it has to get in. Fair enough. I mean,
It's a tiny hole.
as long as I don't damage anything. I'm fine.
Brandon.
The big red bee, it's when I'm always not super familiar with it.
Yep.
It's the one that controls when the parachutes are deployed.
No. What control the pressure is here?
That's only those Raven
Raven
altimeters?
Yes, and then this is the transmitter.
That one's just the transmitter.
Yep.
And there's no cables going between the nose cone and the rest.
It's like self-contained.
Yeah, it's just the battery transmitter.
So as far as sealing it from hot gases through a little like
Okay, the
screw hole, I can tell you easy ways to do that if that becomes a problem.
I think
so. I think you guys will solve that one.
Yeah, like, I imagine it'd be like so quick, and then it's immediately like out of the rocket. And
Well, even then, if you just do it with a screw switch, you'll have a little fun.
yeah.
Oh, yeah, like a cover, right?
Yeah.
Cover, yeah, we need to put this down.
Yeah, I was basically gonna say something similar, or you can just have a bolt through, and as you turn it, it brings something in for contact, and there's the power, it's sealed.
Yeah, that's essentially how the screw switches work too, so like,
Yeah.
basically just that.
Yeah, it's like a bulkhead connection, nothing goes through it.
Easy.
So basically it penetrated. Kind of. Yep, so, yeah, that's basically I think we covered like everything, design and assembly. Yes, we cannot use assembly. Yes.
So the recovery system, the batteries are on the recovery bulkhead, right?
Yes.
Okay, and then where are the switches for that?
The switches, I don't think Steve added now.
Not quite, yeah, but there's enough, or there should be enough space on the underside of the recovery bulkhead to just add them like we did last year. No, like we did in the Xenia one.
Okay, so when we're, like, at what point do we have to? Are the screw switches gonna be with the recovery bulkhead, or are they gonna be with the flight computer?
With the recovery.
Okay, good, so we don't have to wire the things together. Nope, I get it.
Yeah, so just to make it clear, independent, and
So we have 3 completely independent electrical systems.
exactly,
Awesome.
exactly.
You don't wanna wire the cables like last.
No.
It's so fun.
I might have been quick because I stepped out in a second, but you were mentioning earlier that you were either gonna need to vinyl wrap it or paint it in terms of maintaining the aerodynamics of the outside. How does the addition of little set screws that you're doing as part of your on the stand construction affect all those aerodynamics you're just trying to smooth it by adding paint?
So
I
the
mean, I'm not an aerospace person, maybe we're trying to.
So the screws, switches, I don't know how to.
No, I'm not asking what the screw switch is,
Yes.
which is inside, I'm asking what the little set screws that hold the whole
Okay.
engine.
Yes, so they were basically like seat flush on the fuselage.
And they're flexible, not that aerodynamically they're good.
That's something that we really need to look into. We always assume there's no big feedback just because, not a good thing, but this is how like everything do it. Of course, we want to look into like if that actually changes anything, but it would stay flush. So nothing would like extrude up point the fuselage.
They also want to put like 40 volts in the outside for air pressure, so. And they've got other problems than screws for all of it.
Okay, perfect. It was more, we had a lot of questions around what are the characteristics of the supersonic, what's gonna happen to the sticker, all of those kinds of things, and I hadn't heard them addressed in terms of that odor covering.
Yes, so in terms of the wrap, I think based on recommendation, like from Professor Gas, I think we just go with a paint service, so we do not risk anything like peeling off or anything like that.
For your set screws, are you just going directly into the bulkheads? And are the bulkheads threaded, or are you using something like a locking helicoil or key cert to make sure that during transportation from wherever you're assembling it to the launch pad, more likely in flight, that some of these screws don't start moving in or out?
So we're using Loctite on like, when we're doing the final assembly, we'll make sure like Loctite is like security on the bulkhead, and we have radio hose on the bulkhead. I know like it's pretty common in industry to use coils, but based on our design needs, it's more just common to just tap it on our aluminum bulkhead.
And your bulkheads are aluminum, correct?
Yep.
And your set screws are steel?
Or stainless.
The fact you're having them inset and then pulling back out, you may want to think about that. Aluminum does not tend to handle that very well. So that's something to consider, because yeah, like I work in aviation, and that's the number one thing you do is, or not do, is tap aluminum and put in steel screws that you plan on ever taking apart. Because you take it apart, you're gonna start having problems. So
you recommend us using chemicals?
Or something.
Okay.
Yeah, like if it was a one-time thing, you put it in, you fly, you're done. But the fact that you're relying on this to keep your rocket together, that's, I would definitely look into that. Because that's, I definitely have concerns, especially, you know, again, if one-time thing, short flight may not be a problem, but, and like Loctite over a short amount of time, like if you're planning on Loctite fly, that Loctite's not doing much.
Okay.
So
we actually don't need Loctite if we use helicoils.
Yeah, well, if you get a locking helicoil, They have
I see.
free running and walking.
Yep.
But especially if you're planning on using, like I said, you're screwing in, putting everything in, pulling out. Yeah, I would definitely look into something walking. Again, short flight, less of a problem, but it would just suck to have
Yeah.
set screws come out and your rocket fly apart.
Yep.
Unintentionally.
Yeah, why not practice like the best practice, I guess.
Yeah.
I was gonna say Loctite has temperature, like one of the ways you get rid of Loctite is by heating it and to get it apart later, so if your rockets heat up at those extreme conditions, it may not do the job that you need it to do. So I would second that recommendation of some kind of really cool vacuum plate or something that you know is gonna keep your rockets together.
I think Marvin, I think.
I was just gonna say, like, I know we do the thing where we put all the screws in, we slide it in, we back it up, but how do we apply the Loctite? We take the screw all the way out, we apply Loctite, and we put it back in. So why do we have it in the first place?
What do you mean?
Storage.
You mean Loctite?
Like to,
The Loctite, the set screw doesn't take them out.
Yeah.
So.
so why
would
why
we
are
have
they
them
in
access
Bulkhead in
all
the
the-
first place, when we put it in Bulkhead?
Because you don't want like any like rotation, right? When you're installing it, you want something to fix it, and you don't want to lose your screws.
We also don't want things getting in the holes, like if we're on the sandy assembly area. It's
Fair
nice to
enough.
have screw in
You
there.
don't want any feet in the holes, yeah, okay, no, that's fair, but yeah, I've also just been thinking about the fact that we do have heads that are little holes themselves. We might be able to look into some plugs that we can just glue in there or something. I don't know.
Yeah.
It might be a nightmare to get out later. We'll see.
That's something.
That's after, I'm just misremembering in Xenia too, some of the. Radio holes, the radio screws were just like threaded further in when we recovered, right?
Yes, they're not Loctite.
They're not that, but, I don't think that should be a failure mode at all. I kind of think we can just get a magnetic tray and just not drop the bulkheads into the sand to keep them clean. I genuinely don't think, oh, the screws screwed in way too much, so the rocket came apart midair, should be a failure mode, should be a possible failure mode. I think the radial holes should only be deep enough to accommodate the screws and, it's likely to be like this, but maybe a little deeper.
But yes,
like not over.
I agree, but remember Fuselage is like a really thin structure, that means you like the tolerance needs to be very good.
Well, you can make them a little deeper, but like, I understand what you mean, obviously you're right, but like.
Yes, but that's something definitely to like see if there's working. But I agree, like Teleco is something that we should.
Are there any places on the, where we're putting radial holes in something that is a through hole, not a blind hole? Because I remember last year, one of the set screws went in.
Oh, everything is blind, everything is blind.
Okay, good.
Yeah.
Yeah, we flew that one too.
How are you bottom tapping them on poles? Are you tapping all the way to the bottom, or are you only tapping?
Drill them a little bit, but then.
Yeah, and then we just have.
And that's what I was getting at, is you can put a little plug in the bottom of those holes to stop it from bottom, like, so it does bottom out, but doesn't actually bottom out.
Yeah.
I've thrown little like ball bearings from a bicycle in the bottom of the holes before, just to stop me from.
Yes, I think we should look into Telecos and see how to stop them.
But all the other teams just screw into aluminum and steel bolts anyways, not that, right?
Yeah, everything. Yeah, almost everyone just tap in.
This is
Maybe that's a big
So
concept.
1 to 2 time use, right?
Yeah. But in reality, like, because we have assembly rehearsals, that means we also screw in, take it out, screw in, take it out. So that's not good practice, I guess. So
It's one time use during flight, but that's.
it's definitely not one time.
Yeah, the variance not one.
Any other questions about assembly? Right. Conclusion. I'll hand back to you.
Thank you to all the presenters for coming up here and getting all your designs critiqued.
I know it's not easy for all of you, so good job, and thank you for our special guests for coming and providing great feedback. It really helps us create better designs and improve as engineers, so we appreciate your time coming here. All of that feedback should be on the minutes. So, next slide, please. So please go back to the minutes and read through everything ahead of the final design review, which will happen on March 23rd. That is 6 weeks from now. So it seems like a lot of time, but it will fly by very fast. So please plan ahead and make sure all testing is done by then and that designs are complete. So this is the final design review. This is the last time that we will meet as a team to review designs. So of course, there will always be more feedback, but the design should be complete and there shouldn't be any major design changes. Definitely no concept changes after this. Any questions about this? Yeah.
So maybe it's just a me problem, although from what I've seen around, it kind of isn't. I genuinely don't think all testing will be completed for any subsystem before the FDR. I know this is not a right now topic to talk about, but consider.
So this, yeah, obviously things don't always go according to plan. So we have allocated extra time at the end of the season. But this date marks essentially the end of the semester so that we can be ready with completed designs at the start of summer to start manufacturing for flight hardware so that we can begin our assembly rehearsals and make sure everything actually works the way we intended. So obviously try to stick to this plan, but there we can revisit this at a later date to make sure everyone's where they need. Yes.
Couple points. One is having seen both, this was definitely better, like, you know. Pretty good. Like, I like the fact that I have a structure, like the timeline for all the things was this at the beginning. You guys didn't have the like between headings showing where you were in the timeline, the outline. But that's fine. Otherwise, everybody's presentations were pretty well put together today. There wasn't as much. Oh yeah, I didn't put any of that in. That was a huge improvement. Thank you, sir. And everybody did a great job presenting. Even if you didn't feel like you did. I know it feels worse when you're up there, but the only one is there's no final questions. Was there? Is there a slide for like just at the end of the presentation? I think slide go to the very
Final question.
Because I left this out because I wasn't sure where it fit in. So it's Raven 4 altimeter and character deployment business. Did you guys do any programming specifically of those to determine?
You program like the programming is like you open a program and you tell it like your targets basically, and there are some options on like sort of how you want it to detect or how it does backups, that kind of thing.
Okay.
I think we usually just leave it on like the standards, like the default. There wasn't really any super reason to change that. But then we do program like, okay, deploy like main at 1500 and that kind of thing.
Okay. We don't really need to do anything custom because for safety concerns, they have to be like perfectly cost components for hardware and software, and also because this is how they judge how close you get your target apogee.
Yeah.
So while you can fly SRAD altimeters if you really want to, your main altimeters have to be COTS, and that's both for judging fairness and also for safety reasons.
Yeah.
So we don't get to do it that much.
Okay, so then comes the most important part of this question.
the holes you wanna put all over the rocket for pressure equalization. Those are critical for the altimeters to determine their altitude.
Yeah.
Because you guys are going supersonic and so supersonic, you're gonna have pressure waves and shock waves that form, especially near the nose, like on the outside, like the trailing edges of the nose profile. You're gonna have a lot of shock waves that occasionally drift by those holes and create extremely high pressure regions. And depending what your programming does, I believe you guys plan on having your entire rocket body between the nose and the motor being one pressure chamber. Everything.
No, the recovery bulb.
Oh, sorry, everything after the recovery bulb.
Should be one, I believe, yeah, I remember that.
So everything in front, will there be any pressure equalization holes forward of the recovery bulkhead now? Or yes.
So the altimeter takes both pressure and acceleration. We usually set acceleration.
Yeah, well, it'll use both, and it has like algorithms for calculating altitude based on both. But from what I've heard, I don't know if it's like how 100% sure it is, but ever generally the altimeter will look for acceleration for like apogee detection, just because like you can get it by just like we talked about like payload, just like looking as it gets lower kind of thing. And then like it'll take pressure more into account during like the 1500 foot like main deployment kind of thing. Just because of like that, there's like the pressure can be like very dynamic during an entire flight.
Yeah. So is it looking? Does it have rotational accelerometers too? Because your rocket's gonna want to flip around that apogee.
Yeah, I think it's about like 60 hours down. I think it'll be better still.
Yeah, because just the linear accelerometer is useless for finding out. Because you're gonna be at near zero G's for probably 5 to 10 seconds.
Yeah, I didn't need like very accurate thing.
So
exactly.
Yeah. Okay.
I mean, I do know a lot of teams have used like the Ravens.
Yeah.
So like intuitively, I would say like it's probably fine.
I'm not worried about the actual altimeters. I'm worried about the holes and where you put them in my rocket. So the larger the volume that you have equal pressure for, or at least a accurate pressure for, the more holes you need in your rocket. The more holes you have in your rocket, the more drag you have, especially at supersonic speeds, and the more potential places where any defect in your the carbon fiber will want to be laminated with 200 psi. Is there any option to just behind that? Because now, if I go from front to back of the rocket, you have all your parachutes and stuff, you have your recovery bulkhead, sealed point. Your Raven 4s are directly underneath that, correct? Yeah. Any chance of just sealing those in and then having one hole out the side of the rocket, right where you attach that recovery bulkhead?
That would scrap the pad something, I think, because that's another bulkhead going in there.
No, it's the same bulkhead. So you put like this is your recovery bulkhead. Your Raven 4s sit here. You basically sealed hat goes on top of the Ravens, and you just drill a hole through the side and in, so that there's that sealed hat only has access to a hole on maybe both sides of the rocket.
That could be done. Yeah.
That sealed hat needs to be not aluminum or carbon, but
what's the recovery bulkhead? It might be the recovery bulkhead made of
aluminum.
So why can't the hat for the
the hat would have to be
aluminum is like so defining. So like you've got the antenna here, and we need like 3.5 inches to the nearest material that's going to interfere with it. And currently, the defining top of that right now is the recovery bulkhead.
But in this case, you're just making like you could put a Tupperware, right? Oh,
Yeah.
I guess it could be it could be an element. Yeah. Sorry. Good call.
Yeah.
But then you're only measuring the pressure in one tiny little place and not trying to see what's going on.
Just really cuts down on how many variables you have to account for and how many holes you have to put in rocket.
I think one thing you keep in mind is like, I think we should look into if rate report actually is pressure.
Yeah, I think for actually they might be fine.
Yeah,
Like,
not
because I'm pretty sure you can just like seal them and not equalize them, and they probably still work.
I thought it was one.
I thought it was,
Requirement.
yeah.
No, it is a lot, like,
That is it.
because it makes it more accurate.
It is not a pressure equalization. Look at the it's
The other thing is,
create materialize.
Well, find out what the requirements are for that, whether it's because of the altimeters or because they actually don't want you to have a very low pressurized rocket. Like, it's not like it would be anything over 14 PSI, so, yeah, it's not.
the other thing I'm thinking is, even already, it's in the area, so you've got recovery bulkhead here, you've got the bulkhead that holds payload and avionics down here. And you've already got what is in the current design holes for the camera. And that may change, but those holes can double as the pressure equalization. Because once we get close to apogee, like we don't care too much about pressures on the way up. We're able to detect apogee and we record the pressure then. And at that point, like the air is not traveling very fast. So it will be reading good pressures in that area, especially because those holes are so big for the cameras. If they stay holes.
Yeah, I'm still worried about those holes.
Yeah,
because
that's-
I don't know if you've ever blown over the top of a bottle.
Yeah.
Yeah.
But that on a whole rocket body at Mach, those pressure changes will be wild.
You think we're gonna fly a big wizard?
Goes up, Stuka rocket. You just said it's Stuka slide.
Any other questions?
Comments.
Yes.
I've listened to a lot of presentations in a lot of industry and military settings over the years, and I just want to compliment you all as a group. You did a fantastic job. You asked each other questions, you answered them professionally, and you really pulled everything together. I just wanted to.
As always, if you have any further questions, especially about timeline or more admin related stuff, feel free to reach out to Gordon, Scott, or myself, or anyone really. And with that, thank you all for coming.
Thank you.
Thank you.